we are going to get started. Welcome everyone to the first knowledge sharing session this year. As you know, we have 3 of these every year. 2 of them are virtual, and one of them is kind of hybrid. So it's what we call Whitcon in Houston, which we'll talk a little bit more about in a second. Just keep in mind that these sessions are recorded, and the recordings will be also distributed after the meeting today. We also wanted to start with just a couple of updates from us here at Whitson. If you've started to see some new faces in the company the last few months, that's because we have gotten a lot of new faces here. So I'm not going to mention all the names here, but it's a mix of both software engineers. They seem to kind of multiply, and people working more on the petroleum engineering side of things as well. And also one thing that you'll see more of is Jessica will also help us with facilitating a lot of these type of events, webinars, courses, et cetera. So you'll see more of her also in these for us as well. If you've never, or so these people will work not only on kind of coding Whitson PBT, which is our PBT software, but also Whitson Plus. If you don't know what Whitson Plus is, it's a all-in-one web-based solution for everything petroleum engineering related, whether that's DCA, type walls, PBT, bottom hole pressure calculations, RTA, nodal, and well tests. And if you want to learn more about these things throughout the year, we have dedicated sessions on these topics. Graham had a nodal course, for instance, yesterday with almost 80 different participants, or maybe it was over 100. And if you want to learn more about those, if you want to register for those courses as they come and are made available, you can go to our webpage, whitson.com/training, and get more information there. As I mentioned, we have Whitcon, which is kind of our excuse to invite all of you all and meet in person and catch up. We love it because we see that's an arena that a lot of the companies from or friends from different companies actually meet every year. It's always in Houston. This year, the date is set for 2nd of October. It's going to be the same venue that we used last year. So last year, for those that were there in person, it was over 150 people there in person and over 200 people online. And it's kind of just a longer version of what we're going to do today, where we have people that talk and are very passionate about petroleum engineering in general. So those will be topics related to PVT, bottom hole pressures, RTA, flow material balance, numerical models, nodal analysis, you name it, and beyond that as well. For today, we have a packed agenda, so we need to get started really quick. We're going to start with both a presentation, actually in collaboration with the Devon, where Corey and Graham is going to talk about multi-well gas lift optimization, and then we're going to get my Norwegian friend Stein Erik is going to talk about VFP exports, which is something new, but I think it could be relevant for a lot of you, especially those that work on a lot of offshore assets. Milan will talk about downhole chokes. That's been requested a lot, especially up in Canada. They love to put their chokes downhole, and it has an impact on their bottom hole pressure calculations. So he will guide us through that. And then Juan is going to talk about a proof of concept study where we use the Whitson Plus auto forecast. Nils has a surprise presentation, so we'll have to wait with his topic to when that presentation comes. I'm going to talk about something called PNR DCA, and it's just a way to get pressure-informed EURs fast. And Mo's going to take that a step further and talk about auto forecast before Wilson is going to be the second last presentation today, and he's going to talk about how you can use an equation of state to map out properties throughout the basin at scale. And then Matt Jones, he is going to end the session today with I asked, I was at the hydraulic fracturing conference here in Houston, and I asked a bunch of people, what was your favorite presentation of all the technical presentations? And this was the one. So I did it kind of selfishly, and I was like, and I asked so many different people about it, and they always brought up Matt's presentation. So I thought, okay, we need to invite him to do the presentation for our audience as well. And it's a little bit more on the completion side, but I'm very convinced that completion, reservoir production, all of that is intertwined. So having an understanding of that is super, super important. So with that, I'm going to stop sharing my screen, and then I'm going to give the screen and the audio to you, Corey, and then Graham.
Yeah, I appreciate that introduction. Just to confirm, can everyone see my screen?
Yes.
Quick thumbs up. Okay, perfect. So a little background about myself. So I'm a production engineer at Devon. I've worked production for roughly the last 10 years across several basins. And here recently, I work in our centralized production team working on some larger scale initiatives. And multi-well gas lift optimization is something that I've always been somewhat passionate about, and have dreamed about automating it and making it just a little more user-friendly. And it's been a bit of a challenge to do so until a platform like Whitson has come along. So really excited to be working very closely with Whitson in developing this. Let me switch slides here. So a little background on the current state of gas lift optimization. So most commonly, we set compression. It's shared across several wells, and we try to max out the throughput for that given compressor, and we equally distribute it amongst all the wells that share that compressor. And it tends to be a set and forget mindset. The benefit of it, it's fast. However, you can start to see the negative sides of that, which one, doing that, we are ignoring the individual well's productivity. Yes, it might be maybe an 80% answer, but we are more than likely leaving some barrels in the ground by doing that. The less common way and the more methodical way to do it is to look at each well's nodal. So that way you're accounting for each well's productivity, so you can then rank them obviously by their productivity. Obviously you want to set some minimal bounds around minimal injection to make sure you're still achieving critical velocities. And then any remaining horsepower you want to split across the wells in a way so that you're maximizing your production for your given horsepower. Obviously, this can be extremely time consuming to do for one pad, let alone an entire field. The models are going to change with time. Obviously, your reservoir pressure is going to decline. Your injection valve depth is going to move. But obviously, you start moving closer to an ideal state in the form of gas lift optimization. And so the question that would come up is, well, what if we could automate this? And so this is where the power of Whitson has really started to unlock and answer that question. So just if everyone could focus on the right-hand side of the slide. So to see this visually, what we're doing is we're taking a compressor with a given throughput, in this example, 4 million MCF a day, defining how do we divide that injection up to maximize our production. Obviously, we want to put some bounds around that. So, okay, at the point of injection, I want to make sure that I'm meeting my minimal turner velocity. And then from there, any remaining injection, how do I divide that amongst the wells, once again, automatically to increase my throughput? And so this is exactly what this new feature in Whitson is doing. And it's a pretty exciting concept, and we're definitely excited to start utilizing this, getting some pilots underway and seeing how this could impact our production. That's really all I had prepared today to kind of set up the background. Obviously, welcome any questions, but going to be handing it off to Graham as well so he can cover a few things.
Well, thanks a lot, Corey. I'll get my screen shared here, and then I think there'll be an opportunity for people to ask questions at the end for both of our talks. Okay. Do you see my screen okay?
Yes, perfect.
Perfect. So, yeah, Graham Helfrich with Whitson. That was a great introduction. I want to give a little bit of background about, why we do gas lift, but then also a little bit digging in deeper about the method that's going on in Whitson to help ideally distribute a limited amount of gas lift to many wells. So really, when we have our well bore, if we have liquids, water or oil, those are very heavy. And so if our well bore was full of those heavy liquids, we would have a very high pressure drop just from gravity, and therefore we'd have a very high bottom hole flowing pressure, and we don't want that. Once we start to inject gas from gas lift, well, we reduce the density of the liquids. And what that means is it's not as heavy, and we can lower the delta P from the top to the bottom. We can lower the bottom hole pressure. And as we all know, lower bottom hole pressure means a higher rate. So that's really the purpose behind gas lift. But how do you know how much gas lift to deliver to a well, right? It really depends. And so Devon actually introduced this idea of a gas lift curve to us about 1.5 years ago. And if you think about a well that has no gas lift, it typically has a very high bottom hole pressure if there's liquid. As you add a little bit more gas lift, hopefully you lower that bottom hole pressure, add some more gas lift, add some more gas lift. And then this would kind of be like the sweet spot, right? If we have this much gas lift, we get the lowest bottom hole pressure. But guess what? As you keep adding more gas lift, you actually add friction, because all that gas you inject has to come back up the wellbore. So if you over inject gas lift, you can actually back out and hurt your rates. And this really does happen, especially when you kind of set it and forget it, because the natural GOR from the reservoir will typically increase over time, and that can really replace the need for gas lift. And so that's how over injection can occur. So if we take all these bottom hole pressure points and we apply them to an IPR curve, we end up with this green line. So at every bottom hole pressure along the blue line, the IPR will tell us what the oil rate will be, all right? And so really we get this whole relationship between oil rate and our gas lift rate. And the peak of this curve is the highest oil rate we could possibly get from a well at a particular gas lift rate. And so really having this created for each well gives us an idea of our potential, but then we need to show where we're operating today. How does that compare to where we could be operating, right? We can start to quantify what oil rate we're leaving on the table. So I have to say thank you to Devon for introducing this diagnostic to us. It's been super popular. Every well is going to have a gas lift curve, but the truth is each well will have a different gas lift curve. They're going to be unique. And Corey kind of mentioned the word productivity, right? Every well has its different productivity. So these curves will be different. The other things that could cause these curves to differ from each other is the remaining reservoir pressure, even the tubing size. If you have a small tubing size versus a big tubing size, those wells are going to react differently to how much gas lift they need to get their highest liquid rate. All right. So here's the challenge. We have a limited amount of gas lift. We've got wells that are sharing that gas lift. How do you best distribute it? Well, what we're going to look at here is how we use some math to automatically figure out which wells deserve pieces of that limited gas lift supply, with the goal of having the total liquid rate. Let's get into some of this math. Okay, so basically, we're using this function to try to get the highest total oil rate possible in relation to the gas lift rate. This is really just saying, are we limited in our gas lift supply? So really there's two possible scenarios. One is that along the peak of this gas lift curve, that is basically where we can have the highest oil rate possible. And if we happen to have enough gas lift for each well to achieve that, great, then we're done. But in the case where we don't have enough gas lift available, we're going to have to look somewhere else on this curve at a lower gas lift rate. Now, something that's kind of was a surprise is once you optimize and run this routine in all the wells, every well will have its own unique gas lift rate, or the gradient, the slope of this line will actually be the same on each well's gas lift curve, which just is how the math worked out. All right. So, case one is easy, where we have infinite gas lift supply. We can just go to the peak of the curve. But let's say we have a limited amount of gas lift. This is how the routine works. First, we find the peak of the curve, right, for every well, the top. And if we have enough gas available, then we're done to achieve that, right? But if we don't have enough gas lift available to have every well on the peak of its curve, we move on to step two, which is where we change the slope. Ultimately, that means a lower gas lift rate for each well. And if we have enough total supply to deliver that to all the wells, then we're done. But if we don't have enough supply, well, we need to try a lower slope. So basically, we use the CCAT method to explore all these options. And so on the x-axis, this is really the slope along that gas lift curve for each well, where this is a flat slope, meaning lots of gas lift. This is a different slope, which means less gas lift for each well. And then this is even less gas lift down here. So that's what the x-axis means, basically how much gas lift the wells are going to get. The y-axis is really talking about do we have a shortage or an excess of gas lift supply? And if we use this sample on the top, this dot here, because we're on the positive part of the y-axis, we actually don't have enough total gas lift supply to run that scenario. where if we were to try this slope or this amount of gas lift, then we would actually, because we're on the bottom part of the y-axis, then we actually have excess amount of total gas lift supply. All right, so we're trying to find a medium here, doing a bunch of iterations. And so really, just as an example, we try this slope here, which is every well's going to figure out what its gas lift rate will need to be on the top of the, and we notice that when we try this, we happen to be on the positive side of the y-axis, and that means, well, we just don't have enough total gas lift supply to achieve that scenario. So we'll try a different slope. All right, and it looks like we're still on the positive part of the y-axis, not enough total gas lift supply. And then we try this one, this slope, so less gas lift. Oh, now we have excess gas lift supply to meet this this check. And so once we find a point on this side of we can basically start to draw a straight line between these 2 points. Engineers, we love straight lines, and Matthias will tell you that, right? And then we look at these 2 points here, and we do one less iteration, and we basically land at this point here, which is kind of the equilibrium between the available gas lift supply and basically the highest slope we can get on each of the gas lift curves. So that's kind of like the math going on in the background. But what does this really look like when you run it? Well, you're going to input what your total gas lift supply is going to be for a group of wells, in this case 5 wells, optimized. And so the results are here. So what we're looking at, this is the current oil rate that each of these 5 wells is producing, taken from the field, and the current gas lift rate that each of these wells are getting. So it's just a snapshot of how things are happening. Now we'll notice that the total oil rate is currently 714, and the total gas lift rate is about 1.5 million. That's what's happening now. Once you click optimize, what happens is Whitson Plus is going to redistribute that 1.5 million. For example, this first well, it's saying we need to go from the current 216,000 scuffs a day to 1.2 million for gas lift. Okay. And for other wells, we're saying we need to decrease the gas lift going to this well. Now, if we do that, it's saying that there's going to be a prize. And the prize is that we will increase our total oil rate by 270 barrels a day. Right? We're not adding any extra gas lift in total. We're just redistributing the limited gas lift supply to wells that need it more and that will respond. So just if we were to zoom into a case like this well here, it's suggesting we increase the gas lift rate. And if we do, we'll get this rate response, right? We can just check that out because we can look at the gas lift curve for each well. So this is how the well is operating today. The peak of this curve is here, but we don't have infinite gas lift supply. So it's saying that the star is the optimized or recommended place along this curve to yield a big delta in our oil rate. All right, that's one of the wells. Now, if you look at a different well, this well is saying the gas lift rate needs to reduce from 138 to 14,000 scuffs a day. If we do that, this well is going to suffer a little bit. We're going to lose half a barrel of oil a day. We're basically saying, hey, you need to take one for the team because the gas lift you're just hogging could be better used on these other wells. So if we were to look at this particular well that needs to reduce its gas lift rate, this is where we're operating today on this particular well. And it's being estimated that this is the optimized gas lift injection rate because it's going to have a very minor rate loss, and we're going to be able to better use that gas lift somewhere else on the pad. All right. So, Corey mentioned about liquid loading. That can be another reason for gas lift. So that's where this point along the curve is here. That is our minimum gas injection rate needed to keep the well above its critical lift rate. And so you can basically run all this and report what is the minimum lift rate in order to keep all the wells above the critical lift rate. And, in this case, we would need 1.7 million to achieve that. We really only have 1.4 million. So it tells us how much extra gas lift we would actually need to achieve that liquid loading criteria. That's the long and the short of it. This is brand new and it's in your software, but I think we're just really excited to see some results. But the long-term plan for this is that these recommended gas lift rates can be sent to the field and applied. Okay, so whether it's weekly or monthly, that this would be updated and sent to the field. The whole idea is to try to keep all the wells in their sweet spot for gas lift, and that will change through the well's life. Okay, so really that's it. I just want to say thank you, and I'm really proud of how much the nodal analysis has developed in the last year and a bit, and companies like Devon and a lot of our other partners have been key in introducing some of these new technologies and driving it.
My hope here was we can make this a little teaser, and hopefully later in the year can convince Corey to come back with a cool case study as well. But it's been a lot of work, and you guys have done really good, and seems to be a lot of interest related to this topic. I don't see any questions in the chat, so we're going to actually just because I'm always terrible with time, as you all know, we're just going to chug along with the next presentation from Stein Erik. And can you just double check that the sound is working, Stein Erik? And
I can hear you fine. Can you hear me?
Yeah, sound is perfect. And then just try to share the slides and talk about the exports. For those of you, like, I honestly had never heard about that even abbreviation before, but and if you haven't, then we were in the same shoes. But it's extremely common to do, especially for anybody that worked offshore when it comes to creating inputs for simulation decks and whatnot. So yeah, Stein Erik will go through this for you, and he is a fellow countryman, as I say. Sits in I think Oslo and works for a company called Pandion Energy, and I'll let you take it from here, Stein Erik.
Yeah, thank you very much for the introduction. My name is Stein Erik Bertelsen, petroleum engineer as background. Currently, mostly working with offshore engineering. So I'm going to talk about VLP exports for you. This will not be as technically advanced as the previous presentation. It will more type of guide you through how you can generate VLP curves from Whitson to use it in other softwares. Okay, then I will try to skip to the... Can you see my slides okay?
Yeah, slides are great.
Yeah, and please, Matthias, since I'm very new to the Whitson universe, please drop in if you have something to help me out and fill in with additional information as we go along. Yeah. Okay, yeah, Pandion Energy, we are a rather small oil company. Our assets is in outside Norway, offshore Norway. I'll try to make a pointer here. That's the location of one of Whitson's headquarters, Trondheim. So we are our assets is just outside the coast of Norway. Our path into Whitson was probably quite different from most of your clients. We were looking for advanced PVT and knew about Whitson PVT, and then we also asked about, okay, simplified PVT. When we have limited data, we would like to have that as well. And Whitson, you then suggested Whitson Plus, which was new to us. And okay, this was interesting because you also have RTA and VLP and other capabilities we were interested in. So that was our path into Whitson Plus actually. And this presentation is going to be about the VLP export. We are really Whitson rookies. We started using it in February 25, so it's less than 2 months. We have been working with Whitson to enhance the capabilities with the exporting these lift curves. And why do we need it? We need these lift curves to as input for reservoir simulation. Okay, and both wellbore and pipeline modeling is essential offshore Norway. Here you can see different layouts for the fields. So we need to calculate the pressure drops from the wellbore up to the seafloor, and also in the production network to either a floating production facility or a platform. Artificial lift, it's not pumps. Normally it is gas lift. And we also have water and gas injections. And the permeabilities, they are quite high. It can be down to 1 mid-Darcy, but mostly it's much higher than that, up to 10 Darcy, for example. So these are just some examples. Okay, I'm not going to go much into the details about IPR and TPR, or VLP, I mean. First of all, there are different ways to different terms about vertical lift performance. We have VLP, TPR, and VFP. So I'm generally mostly using these, and Whitson is using this one, VLP. So that is my new way of pronouncing this. You are familiar, I guess all of you, with a pressure profile from the bottom of the well up to the wellhead, like this. And here we have the IPR VLP curves combined together, as you are very familiar with working with in the Whitson Plus software. Okay, just one note here. It's like this liquid loading, the unstable region here, can cause some trouble for numerical simulations. And I've seen, not very frequently, but it's not uncommon either, that either the engineers or a software vendor implements a straight line VLP here to avoid numerical instability when trying to simulate the performance. So just be aware of that. And it's no problem if you are operating out here and still this one can, in the iteration, can cause instabilities. It's a prudent way to do it. But if you're approaching here, and then this instability region should have the VLP curve going up here, so that you are not not too optimistic and not make it straight line. Okay, this is the old workflow. I'm not going to go very much into detail here because there is a new workflow we have been working with. And just let me try to zoom in. Okay, that was the wrong direction. Okay, this one is in the numerical model screen, like you can see here. I'm not going to go through all of it. You can look it up on the video afterwards, I think, if you want the details. But the old process here was quite tedious, not intuitive, with sort of a lot of windows to follow. This was the first part. If we go to the next one. Okay, this is just following up. You have to do all of this stuff in order to get to the point where you could generate the VLP curves in Eclipse format. Okay, so this is the end of it. This is something you can import, for example, to a reservoir simulator down here, the final step. We also saw that, okay, there was a little bug there, but that one was only related to not the pressure calculations as such. It was just a reporting bug for the actual rate. So we had to do some manual updates afterwards, which was really simple, but it was a little bit annoying. We also saw that the instability region was treated with the straight horizontal VLP lines. So Whitson addressed that. And then we came up with a new workflow. It has just been rolled out. This one is here at the screen with the bottom hole pressure, like here. So then it's, it's more type of, we are going into one screen where you can update everything. Like it's the bottom hole pressure here. Okay, so you have to, there is something called VFP export up to the right here. You can push that one and choose the well configuration, the flow correlation, and the setup to generate the VLP ranges. And you can also define the artificial lift, either gas lift or the pumps. And then you are ready to go. And you can also then choose to have the instability region on or off in this new setup. And then it's rather simple to generate these new files, and you get these new files out in Eclipse format like this. Okay, so this is just a VLP export file. Okay, and here you can see the results plotted in another software than Whitson. It's the reservoir simulation deck. This was the old workflow. You can see the VLP profiles like here. If you look at the new workflow, this figure here is similar to the previous workflow. But if we add that we can have the instability region also preserved. It looks like this. So then you have the choice. You can choose if you want the output with or without the instability region in this new setup. I think also Whitson is going to make a few more improvements on the capabilities for the parameters we can use to configure this VLP format. Okay, I think yeah, that's it basically.
Oh, perfect. And I think this was kind of an FYI for a lot of you the companies we work with. We work primarily with you on tight and conventional. So for instance, the old workflow was not really a workflow because it was kind of all hidden. It was done automatically behind the scenes for those who would actually use these tables in the background. But here it was basically a new use case where we actually wanted to generate this to be used in Eclipse, which seems to be very, very common to do for a lot of offshore workflows in general. So the rate bug, for instance, was because we use a symmetry of element method. So we scaled the rates down by a quarter of a frac and also accounted for the number of fractures there. And a lot of these, at least for those of you who needs these VFB exports in a very simple format now, it's literally just one button and you can configure everything in one screen and you can generate it directly where it makes sense to edit these things, which we think is in the bottom pressure part of the software.
Yeah, I think Matthias, it hasn't been used a lot because this bug with people would have noticed it right away.
Exactly.
So yeah, so it wasn't a really big problem, I think.
No, excellent. We're still on the production engineering train, so we thought to, since the production engineering tends to have a lot of equations, at least for a simple mind like myself, we're going to keep it to production engineering, and we're going to go from one production engineering topic to another with Milan here, which is going to talk about downhole chokes, which is also a new capability that is relevant for a lot of you. And Milan is sharing screen, perfect. And then can you also just unmute Milan so we can see if we can.
Can you see me now?
Yeah, perfect, excellent. Okay, I'll just mute myself here.
Can you hear me and see my screen and the pointer? Yeah, so I want to talk about downhole choke. So first, that is coming soon to Whitson Plus. Here you have a sneak peek of how it will look like. So when you specify the well data, the well after the deviation, you will get the option here to specify a choke. So I have a little video here to play. It is essentially, you have two options, wellhead or downhole choke. Then if it's a wellhead choke, it's going to take data from the production data, essentially the choke size and the line pressure. But if you are using a downhole choke, then you have to specify the measure depth and the choke size. But that's how. So it's hopefully will be soon. The backend implementation is ready, and the front end it's already very advanced. So hopefully you will have it soon available in your version. Yeah, but you have those two variants. It's essentially wellhead and downhole choke. Wellhead taking data from the production data you specify, and downhole choke, you have to specify it here in this window as part of the completion. Yeah, so just to give some basics about choke. Choke essentially we use to control rate. If we want to produce at lower rates that open choke will give for some reason. And essentially we have a lot of complicated designs of chokes, but essentially if we want to represent all of them, it's a contraction. So simply we reduce the cross section, we accelerate the fluid, and then we drop the pressure, and the hope is that pressure will remain low. We don't get any significant pressure recovery at the exit. That's kind of the purpose of the choke. And to understand how it's working, I suggest we do the thought experiment in which we, keeping the inlet pressure constant somehow, we are going to be changing the outlet pressure. First, we keep it at the same inlet pressure, so you essentially have no flow. These two pressures are the same, and then we're going to be reducing it and see what happens. So here you see in this chart, we have with time, the pressure here at the outlet. Initially it's inlet pressure, and I'm here just at the origin. And this chart is just showing you how much rate are you getting with the delta P across the choke. Okay, so initially if the two pressures are the same, I have no delta P. As I start lowering it, the delta P is actually increasing. Okay, so I lower the pressure, I get a higher delta P, and then I get more rate. So that behavior, it will be non-linear, and it's going to be kind of the rate I'm getting when I increase the delta P is higher and higher, until I reach something that is called the critical conditions at the throat. Essentially, the fluid, the velocity here at the throat is traveling very, very fast. And at that point, essentially, doesn't matter how much I drop that pressure, simply that rate is not going to change. It's going to remain constant. That happens at when the delta P across the choke is approximately, usually, typically, I will say around 50% that pressure. If you go below that, the delta P is greater than that. Essentially, you're going to get like simply a constant rate. So that's a bit of the complexity of the choke. You are operating in two regimes. One is called the subcritical regime, in which is nonlinear. If I increase the pressure drop across the choke, I will get more and more rate. But then after that, I will get to a critical regime, in which it doesn't matter how much I vary the outlet pressure of the choke, simply the rate will remain constant. Okay. If we do a change in inlet pressure and do again the same experiment, we try with a lower inlet pressure, we are going to get a similar curve. But since the inlet pressure value is changing, so now the critical delta P at which critical flow occurs is actually going to change as well. If you remember, it was a 0.5. So if I have a lower inlet pressure, then the delta P is going to be lower as well. Okay, but essentially keeps the same shape. And if I change the opening, which we have to do with time, we get less energy from the reservoir, and then we typically have to do some adjustment of the choke, then it's going to look like this. If inlet pressure is constant, and then I use a smaller choke, what will happen is that I will get a smaller rate. Okay, but I still get like the subcritical and the critical region. Yeah. So something about planning. So I wanted to include here some comparison between wellhead and downhole choke. What is the difference? So consider we have this well here. We have it's very close to the separator, and we have no choke. So we can assume that the tubing head pressure is simply equal to separator pressure. And we have a tubing, and let's say it's very close to the top perforation, so we can actually plot the IPR and TPR or VLP in the same chart. If we were going to produce this well in this configuration, we can use nodal analysis to calculate how much that will be. So I have a IPR, what comes from the reservoir, and then I have my TPR, is essentially what pressure I need to flow against separator with a fully open choke. I am going to get that this plot of pressure versus rate, and that will be my equilibrium rate. But if I don't want to produce there for some reason, it's too high, too much sand, I will start dragging too much gas or too much water, then I want to operate at some lower target rate value that it will be better for recovery. So then I need to actually move these two curves, shift these two curves to achieve that intersection. So the way we do that with wellhead choking is that we start to change. Let's say if it's an adjustable choke, I start to close the valve, or I simply just change the beam. If it's a fixed positive choke, a beam size, I just have to use like a smaller size. And then by doing that, what I will do is I increase the tubing head pressure, and by increasing the tubing head pressure, actually I shift the VLP a bit higher, and I achieve this intersection until I achieve the intersection that I want. Okay, that's essentially the what happens in wellhead choking, and I think it's interesting to look at the profile of stuff in how variables change along the tubing. So you see, in this case, you have the pressure that gives you the bottom hole pressure here at the top perforation that gives you the rate that you want, and then you will have a reduction of pressure due to the flow of the fluids through the tubing, and then suddenly here at the wellhead you have a drop in the pressure to reach separator pressure. You have like at one point drop in pressure. Velocity actually follows a different behavior, going very differently. So velocity here is because you are at a high pressure condition, velocity is usually low. And then when you reach the top, then you have a sudden expansion and velocity becomes quite high. It's a big difference in an increase in velocity. And temperature coming in here is the reservoir temperature, essentially. Then you have a reduction in temperature because you're losing temperature with the formation. It's getting colder. And then at the choke, you have a cooling effect that can be significant, quite a few degrees, is essentially depending on how much gas you have on the stream. If you have a lot of gas, you have what is called this Joule-Thomson effect, and then it can become actually quite cold, and you can actually form hydrates or even ice. Now let's take a look at the case of downhole choking. Now let's say we're not going to use any choke up here. We want to put some choke down here, but we want to have the same effect. Essentially, we want to operate at the tubing head pressure, which is equal to separator pressure, but we want to achieve the same effect. So essentially, this curve, what it tells is that you have high energy. The energy, if you want to produce that rate, the energy you have from the reservoir, it's high. But the energy actually you need to produce against separator is not that much. You don't need actually that much. You need this much. So what I need to do is I need to create a discontinuity here. If I want to achieve this intersection, I actually have to drop the energy down to this level. And that's what I can achieve with the choke. The choke, essentially, we can do take into account the log profile in the tubing, and I can insert an insert, essentially is a reduction in diameter. Or if I want to make it very complicated, I can use some sort of valve that I can actuate from the top. But essentially, it's a restriction. Both of them operate in the same way, a reduction in the cross section, and then I'm reaching the energy. I have more energy than what I need, and then I drop it, and and then I reach to that level, and then it can continue flowing. So that's the difference between both. And but looking again at the variables, how they're going to change now, I have put here the previous we did for wellhead choking. They are in these continuous lines. Okay, initially high pressure, and then you have a big drop at the surface. But now here will be opposite. Actually, now here at the bottom hole, you have the drop because the choke is there, and then you have that the pressure continues to reduce. Velocity, on the other hand, it's when you have the choke here, you have an increase in velocity. It's not that significant like in the wellhead case, because you still need to have a significant pressure to flow to the surface. But then you have that when it's expanding, the pressure is reduced, then the velocity is increasing. And the temperature, the same thing. You also have some cooling effect, but that cooling might be less pronounced at the bottom hole, because actually you're expanding from a higher temperature, which is close to formation temperature. And then the temperature is dropping as you lose heat with the formation flowing to the top, and then you reach the top, and there nothing else happens. So that will be the difference in your profiles. And you might argue, depending on your case, so why to go through all the trouble to put downhole choke? Well, one thing people say is, well, the temperature is a big factor. If I do it at the surface, if the fluid is already a bit colder, and then when I expand, it gets even colder, so I can reach the hydrate formation temperature. While here, since I do it in hot conditions, essentially I might avoid entering into the hydrate region, formation region. Some other people say that due to liquid loading. So for example, here you see that in the wellhead choking case, I have low velocities. When I choke downhole, I get higher velocities, which could be beneficial actually for liquid loading. But one downside is that I might have more erosion, since now I have higher velocities in the tubing. Another thing is also that the stress, so pressure in the wellhead choking is higher. The pressure levels are higher throughout the whole tubing than in the downhole choking. So you can use whatever argument you need to have which choke would you prefer. So that's it. I was told it has to be short, but just the takeaways. Chokes are coming soon. 2 versions, downhole and wellhead. Wellhead taking data from production data, choke size and line pressure. And downhole, you have to specify the depth, and you have to specify the size. Chokes are quite complicated due to these 2 regimes that you have to take account for. And then that will allow you to evaluate the downhole and wellhead choke conditions. But essentially, what is coming into the choke is at different conditions: pressure, temperature, velocity, and that will affect how the choke will perform. That's it. Thank you.
Excellent, Milan. It's perfect. Learned something new today. Why people would do it. I was like, why go through the bother? But it's clear to me now, so at least I can try to explain it. Any questions? I don't see anything in the chat. So so the ETA on downhole chokes in Whitson Plus, I saw there was a lot of applauses, and I tracked them, and it's a lot of the you Canadians. We're getting Jessica's Canadian now, Graham and James, and we're getting more of them in the company. And I know a lot of you guys love that and want it in the software. I think it's actually, we discussed the next release just before this fall, and I think the next release is next week. I'm going to double check on that, but maybe as early as next week, Brett. Maybe as early as next week. So I'll double check that on downhole chokes. As we have so good, and of course Brett is up in Calgary. Maybe it has to do something with the weather, why it's so popular up there. It's I don't see it that much down in the US, but I might be wrong. Very good. We have great momentum now, and we're going to switch gear from very kind of production engineering heavy items, and we're going to go a little bit more to day-to-day forecasting. The next one that's going to present is one from Oxy that we've worked with a lot the last few months. It's been a lot of fun. I've been lucky to know him for a few years, but haven't been able to work with him that closely until recently. So it's been really enjoyable. He sits up in Denver, and he will run you through a kind of a POC workflow that we have been working on together. So with that one, I'll let you take it away.
Thank you so much, Matthias. Can you see my screen?
Yeah, and hear you perfectly.
Okay, sounds good. Okay, let's get into it. So a couple of things. So our team has historically leveraged oil EURs, gas EURs for both operated, non-operated wells across various types of analysis that are common for various things for many operators. Some of which include individual well performance and surveillance, pad type optimization, to the point where you're trying to maximize the data utilization to inform how you build your tie well profiles or tie curves. And not only that, also to understand how can you inform the next pad that will be developed, not just from an individual well performance, but also from a section level optimization. These EURs can range from actually using the EUR for a given well, to the point where you're trying to not only use that, but also use CUMs at 12, CUMs at 24, various time steps, because sometimes, tail effects, can lead you to believe something that may not be necessarily super helpful, especially at early time. So, we can all agree that, EUR utilization, it's important for us, for everyone, and also to understand how you can use those when you're trying to look at across the fence. So automation, obviously, it's an important thing. We can go in and do DCA or any form of forecasting on an individual well basis, but that can be time consuming and subjective, right, based on the analyst. In the past, we've implemented automation to manage bias going into it, but at the end of the day, we've delivered tools that have been well established and have been utilized by many stakeholders, so that we can do the analysis that I mentioned before. That being said, the way that we used to get EURs for especially for non-op or competitors was informed by using data providers that are very well known in the industry, but some of our internal initiatives have been to sort of curate those partnerships and help us, do a little bit more with less, because sometimes, more is not necessarily better. With those changes, obviously, you've created these tools, many Spotfire, files that have been created by the individuals, by teams, but as soon as one of these data sources gets retired for whatever reason that might be, obviously things can break. So that led to us, exploring alternative solutions. We started to look at, some in-house, products that we could leverage. Also use the existing data products that we get from some of our current providers. But at the end of the day, perfection doesn't exist. We encountered discrepancies, especially when you take those products and you compare with internal estimates. Not to say that internal estimates are, the gospel, but obviously we want to make sure that we can still attain some level of directionality when looking not only internally, but also looking externally. So as a result of these challenges, we started to investigate alternative forecasting solutions, and that led to looking at Whitson Plus. Whitson Plus has an auto forecasting module, an auto fit, from an individual well basis that's very well known. in the application. But one of my colleagues initially did a super quick benchmark to look at what Whitson Plus could deliver from an auto forecasting standpoint compared to internal. And, we were intrigued by the possibilities. And that led to putting together a proof of concept, which is going to be the main topic of this presentation. So initially what we did, this was a manual process, and I want to be specific about that because that's what we don't want to do. Although we could do this, every now and then, it still requires human intervention, but, for the sake of the POC, that was okay. So what we did is that we used one of our data providers. Whitson Plus has this app project at the bottom, at the top right, which can allow you to connect to many different data providers. And that way you can bring in wellheader data, production data, and so forth for many types of analysis. But in this case, given that we're trying to create a data file that is inclusive of both operated and non-operated data, that obviously translate to leveraging monthly production data. So in any case, we brought in, that data set, 2,000 plus wells, along with their production. Then one of the steps that we do want to implement in our workflow is to make sure that we are intentional about the way we want to do forecasting, especially when it comes to the formations that are of interest for our development. Not all formations are created equal. Obviously, when you look at your strat column and you started take a look at the reservoir properties, perm, et cetera. In the context of unconventionals, we can still deal with tight sandstones, some conventional formations, and given what we know, we believe that we can be a little bit more specific in the way that we want to do auto forecasting for these formations. So in this case, you can see that I created formation-specific groups, which is something that you can do in the application, provided you have the formation in the wellheader data when you bring the data into Whitson Plus. And that was available for us. We created these subgroups with specific well counts for each of the formations that you can see on the slide. So once that's done, you can get in on every single one of them and set them up as you see fit. And this is where you initialize everything for auto forecasting. Obviously, you have an opportunity to set these ranges as you see fit, not only for oil, but also for other streams. In this case, the focus of our POC was oil, but we also plan to extend this for more gas specific primary formations. In this case, you can see that you have different options to set the way that you want to do this. You can also feed partial data in the case of giving more weight to late time data as opposed to early time data. But for the sake of the POC, we wanted to keep things super simple and get to the point where we could do benchmarking, our EURs with the product coming out of Whitson. So if you're still with me, the next step is simply hitting AutoFit. And this AutoFit feature runs very fast. I mean, it's impressive, the speed of how these calculations can be done. A couple of things to highlight on this visual here. You get essentially a well header that is inclusive of all the features that are relevant to a DCA forecast. So you can see peak rate, different declines depending on which one you want to use for whatever analysis you might want to do, B factor, the limb, et cetera, et cetera, et cetera. What I find also very beneficial is to get a feel for the error, both on the rate and more helpful on the cum side of things, because obviously the rate error can be influenced by downtime and things like that, where the cum side of things, data is smooth just by the nature of looking at cums. So that can be helpful. You can sort these things and actually click on a well of interest to evaluate the goodness of fit. That's pretty good. And in some cases, you can actually click on a well and do some manual edits to get to the point where you get a forecast that you feel more comfortable with. Now, all of that is good, but again, we're still living in the world of manual or human intervention. Okay. So the next step that we did after getting this summary, it's exporting the data, which you can do just by clicking on that guy. And then what we did is that we compared the results from Whitson against our internal estimates. Again, I want to highlight that just because those are internal estimates, those are not necessarily, again, the gospel, right? But it's our best estimate given our intuition and the things that we know, for a given formation, et cetera, et cetera. But when you take a look at this plot and you spend 1 minute looking at it, my intent is not for you guys to look at all the statistics that are shown above. But again, just by looking at this, using the defaults from Whitson, not tweaking it too much, we were really impressed and encouraged by the possibilities, okay? Being a POC, we didn't want to spend, significant amount of time chasing perfection. We wanted to see, okay, does this even work? And for our case, it did. So the next step was to, have some internal conversations, where do we want to go from this? And that led to engaging Whitson. So I had some discussions with Matthias and Henrik, who has been also critical on where we're at in terms of these phases and where we're headed. So I'm going to walk you guys through phase 1 and phase 2. Phase 3, it's on the horizon, so we won't spend too much time on that, but we'll share the vision. So for phase 1, this one actually took a little bit of time because Whitson not necessarily has a partnership with the data providers that we do have a partnership with. So Whitson has access to our databases. So what we needed to do early on was we want to create an evergreen connection with our data sources. Which data source is the one that might be the most optimum for what we want to do? So we spent some time doing QA, QC, a few iterations between Whitson Plus and ourselves, and we landed on the source that will be feeding this workflow. So that was good. Then we also wanted to make sure that we were not bringing or saturating the Whitson Plus platform with unnecessary data. So we spent a little bit of time being intentional about how to filter and how to set things up for success. And finally, given that this is still a POC, we also, not necessarily a POC, but given that we are still working on this, we wanted to sort of keep the effort contained to the reservoir engineers that are taking a look at what we're seeing. In addition to that, we saw an opportunity to share some ideas and perhaps enhancements for Whitson Plus to consider. One of the things that we wanted to include was months of production because the quality of a forecast, it's directly informed by the available data that you have. So having a column or having a feature that can capture the months for a well's production was good for us because that can also help us understand the errors that we're seeing. Because if the error is significant, maybe that's simply an artifact of not having enough production for a given well, especially erratic production for a well early on. In addition to that, we don't only value EURs, but we also value additional time steps because those have led to various efforts, especially around multivariate analytics, where you can see the importance of a given feature more so at early time than at late time. So as you can see there, we made a request to, hey, Whitson, can we include 12, 24, 36, 48, and even 60 months to be included on that export that I showed in a few slides back, and that has also been included. And for this one, we're giving weight to actuals, but if the actuals are not there, then we're using the forecast as plan B. Now, the last one that is highlighted is something that Whitson has already released to the public. One of the things that I mentioned before is that sometimes you can see a well and you may not be super happy with the forecast. You can go in and you can edit it, but the next time that you want to run the auto forecast, you don't want to overwrite the adjustments that you did. So as a result, we made the request, hey, can we add a flag? Can we do something to make sure that doesn't happen? And that has been completed. So that was good. Now, where we're headed from an automation standpoint, this is still a work in progress. As a matter of fact, we plan to meet next week because, automating the forecast in Whitson it's good, it's fine, but the publishing of the data, that's going to be the game changer for us because we want to make sure that not only we as a team leverage these data, but our stakeholders are presented with consistent and ready to use EURs for whatever application might be. So like I said, this is still a work in progress. We see an opportunity to deliver a product in a database where we can keep track even how these EURs are changing as a function of time with version control features added to it. But this is going to be my last slide. Ready to take some questions or any thoughts from the audience.
Excellent one. And again, a lot of these things are actually coming in the release next week. So for instance, the edit thing, it's brilliant because I've been there myself. You launch the auto forecast and you sort on errors, and a few of the wells that have like a pretty big error, you want to kind of go in and make sure that, maybe it was like one of the few wells where there was like a frac hit or something funky going on. So you want to go in, edit it, and then instead of having to then, and kind of lock it in stone, and when you now would go in and auto-fit again, it will be overwritten. So that it's just a way for you to be able to control that the manual ones that you've done, kind of happy with them, that's a part of that auto forecast, and you can go and like iterate on B factors and whatnot. You don't have to do that again, and it's one of several upgrades that we made with Juan, and of course Henrik from our side who's been the lead on the auto forecast side of things. Perfect. To see some of these things in action, I would stick around for most presentation that comes up now in the 30-ish minutes, because he's going to show you a few of these things in action. But Juan, super appreciated, and very, very good presentation. And my hope, and I'm saying that in front of all of you guys, since it makes the stakes a little higher, is that Juan could come back and convince him to fly down and hang out with us in Houston for WhitCon to look at where the status of that project is. Now we're going to go to the only surprise presentation we have today. And some of you might ask, why are we not releasing the title before the presentation? And some of you might think, oh, it's just like to increase the excitement before the presentation. But the truth is, Nils was out on vacation last week, and I had to make this little flyer thing to pass it around before I knew actually what his title was. So we'll all appreciate and enjoy it live here now. Nils, if you can share the screen and unmute, and we'll just take it from there.
Sounds great. Can you hear me?
Yeah, sounds excellent.
Awesome. Well, I'm a little worried with the surprise comment that you might have a little overhyped my presentation. So, but nonetheless, I'm excited to be here. Always appreciate these kind of knowledge shares that Whitson puts on, and hope that I think what I'm presenting today is kind of pretty simple, but it puts a couple of examples kind of to what Whitson, a lot of the different Whitson personnel kind of talk about a lot on a daily basis. Just providing a few practical examples of kind of how we use kind of analytical RTA here at Continental Resources. So currently, just a little bit of background on me. I work at Continental Resources. I work in our kind of strategic growth group right now, but in a previous life, kind of where this is coming from, I worked in reservoir engineering kind of across a couple of different basins. So well, with that, I will jump into it. Just to give a little bit of an overview of kind of what we're looking at with this data set. These are dry gas wells. I kind of love to do analytical RTA in some of these dry gas wells just because some of the trends are so clean, and it's pretty easy to get some tangible values out of them. And so I loved working and doing all sorts of kind of views, kind of particularly on this asset. These wells are pretty deep and overpressured, looking at over 13,000 TBD. The well set kind of takes into consideration a lot of different vintages and kind of lateral lengths. I would say a majority of them are in that 2 to 3 mile range. And in this analysis, we're only covering one specific formation. And just kind of the objective I had kind of going into before I performed this analysis was just kind of a lot of things we deal with as reservoir engineers, trying to, I think everyone gets asked very early time in the well's history, how a well is performing and if it's performing up to our expectations. And so being able to kind of understand how a well is performing early time, and if there's any potential damage impacts early time as well. And then also being able to kind of optimize our development. Two of the things that I look at a lot are always depletion and density. So just a little bit of kind of the setup that we had in Whitson going into this. As you can see in the top right-hand corner, this is clearly a dry gas reservoir. You have both your separator and initial reservoir conditions well above kind of your dew point. I love that graph in the bottom right-hand corner because it just shows you kind of clearly how clean some of these trends are in the square root of time plots that you have in classical RTA. And then I also just threw a plot on to kind of highlight kind of some of the different bottom hole flowing calculations and kind of how they compared. Just as an FYI as well, these wells are flowing up casing initially. So this is kind of a little bit how we use specifically the classical portion of the analytical RTA. There's a lot of different takeaways and probably could spend a lot of time here. I think some of the strong takeaways I find interesting from these different graphs. One is that specifically in this asset, we can find a pretty clean correlation. It's more linear when you look at the LFP versus 365-day cum. It's almost a linear line that you can fit between an LFP and the 365-day cum. And then there's also a pretty strong correlation that we see internally between LFP and gas EUR. It starts to become a little less non-linear, kind of towards the tail end, kind of the higher LFPs, but kind of serves as a pretty good prediction tool. One of the other kind of important things that we look at a lot, especially in these dry gas assets and being overpressured, is that not all LFPs are created equal. We see unique trend lines for a variety of parameters. The one I kind of highlighted here that I think we take into consideration very often, specifically in this asset, is whether there's depletion or if there's no depletion. Kind of what I mean by that is just whether you have kind of a parent well within about 2,600 foot of kind of the infill wells. And you can see that there's kind of a unique trend line between LFP and 365-day cum as well as LFP and gas EUR. So something important to take consideration when you're kind of comparing kind of LFP wells that kind of there's various different correlations between those. So, and it's also interesting, I thought, that kind of at the lower LFPs that you don't see as much of an effect on distinguish between the depletion and no depletion case. And then just another side note that I think is interesting as well is that we did sort of a LFP versus SOFH correlation, and you can see that there also is kind of a linear correlation that kind of then topples out kind of at larger LFPs over here. So some interesting takeaways and kind of help our understanding of kind of when we're infilling wells around depletion, as well as kind of understanding kind of what's affecting our LFPs in our development patterns. And then kind of another thing we do a lot, this is a little bit more on the fractional RTA. Kind of as we were doing this analysis, one thing we noticed is we had a well that kind of was underperforming our expectations, and we wanted to kind of understand why. And I think there's a lot of interesting takeaways from this well as well. If you look in the top right-hand corner of this square root of time plot that we had in classical RTA, you can kind of see the kind of buildup of the well, and you can see that interestingly enough, there's this like rollover effect almost early time in the well, and you can clearly see that there's some sort of skin factor kind of on this well. And if you look at it in fractional RTA, kind of in the bottom right-hand corner, you can see that kind of early time, you're seeing a delta that is above that 0.5, which suggests that you maybe have some low fracture conductivity, something doesn't seem right, not typically what we see in a lot of these wells. And so when we saw this, we decided to go in and perform an acid job. And what you can see here is that after the acid job, both the square root of time plot and the fractional RTA plots both change. So on that fractional RTA, you see the delta kind of then enter a kind of a 0.5 or kind of a infinite acting linear flow regime. And then you see potentially some of that skin factor kind of disappear as well. And then kind of plotting it a little bit on what we had before, you can kind of try to derive a LFP after the acid job, and you can see that that falls a lot more kind of within the trends of what we anticipate between like an LFP and a 365-day cume. So I know that was short, but we love using analytical RTA here at Continental kind of for some of these dry gas wells, and they really help us diagnose and kind of understand optimizing depletion, density, as well as kind of being able to identify how our wells are performing early time. So with that, I'd be happy to answer any questions that anyone might have on any of this.
No, perfect. You mentioned like this thing that I hear all the time from buddies working in the industry, and it's the wells come online, it's produced just for maybe a couple of weeks, and they get questioned like, what's going to be the EUR? Like, how good is this of a performer? Do you guys kind of use a range of different techniques for that, or do you use primarily this, or do you have like a favorite for these type of wells yourself?
Yeah, I definitely think we have a range. Whether it's pressure normalized forecasting, which I know you'll talk about. I think this is just one additional. It's kind of a supporting technique that we'll have. I think luckily these wells being high pressure, they do IP and start to draw down pretty quick. So you're kind of able to get, based off the production, you're able to understand pretty early time how they're performing. But I think having some support with kind of some RTA is always very beneficial. So
we also got a question here from Jorge. Have you seen the contacted OGIP? If so, how does it compare with the Sophie H relationship? Is it linear or all scatter?
Sure. Yeah, that's a great question. I will say with particularly this area, trying to hit boundary dominated flow, it takes a little bit of time, so there's less data points when you get to that. But there definitely is a correlation, similar correlations actually between all these graphs, and if you use contacted pore volume. Just the intent of this, of course, why I highlighted this, was just trying to get, before boundary dominated flow, if we can kind of understand how these wells are performing. So perfect.
Just on your depletion wells, are you using a lower initial reservoir pressure when you do RTA on those wells, when you calculate RMPs and stuff like this, or do you keep them the same as the non-depleted wells, quote unquote?
Yeah, it's a great question. For this particular analysis, we used a similar initial reservoir pressure. So
very good. And Juan also wondered how you exported the LFPs and whatnot out of Whitson Plus. Was it through a backend solution like the API, or did you use the front end?
We are working on a backend solution, and I definitely believe that's where we're headed at Continental. Being able to kind of pull that on demand a little easier. I just went through the Whitson program and kind of some of the export kind of parameters that it has on the main page in order to export these. So
perfect. Okay, my last question on this, I just I'm the next presenter, so I'm going to delay it for myself. But how do you tag a well as this is a depleted well versus a not depleted well? When you do those distinctions, how do you actually assign that metadata to these wells?
Yeah, so specifically in this analysis, when I highlighted the red versus kind of these blue wells right here, it was around 2,600 foot. A little bit how we determined that, though, was with kind of frac hits and where we're seeing communication with the parent wells when we kind of stem these initial wells, and where we believe we're trying to kind of contacting them, if that makes sense, at a minimum. So
no, excellent. And I think this was the perfect segue. It's almost like a planned this, and it's honestly completely randomized and trying to accommodate for people's schedule throughout the day. But I'm going to talk, it's a little bit to the one thing Nils mentioned here about, if you only have early time data and, your bottom pressures are changing, is there a quick way for us to get EURs? And that's what we are going to call it PNR DCA. That's what Oxy has also called it as well. And for those who didn't attend this webinar last month, is essentially what was presented there by Oxy. So in short, what is PNRDCA? Well, what it is just pressure-informed EORs that you can hopefully get very, very early. And in this presentation, what I'm going to try to do is kind of first of all explain to you what is PNRDCA, like what's the 101 there. The second thing is a potential workflow. So we haven't released this in Whitson Plus yet. I'm still kind of testing this together with the colleagues night and weekends to try to come up with like a consistent workflow because it's a little bit more tricky than I thought initially. And then we're going to talk a little bit about how you could take it from this like rate and pressure space and translate into potentially rate time. And that's just an idea. Maybe we can get some thoughts from the audience as well. But PNRDCA, if you didn't participate in this webinar from Xueying last month, the link is here, and it's basically her and her colleagues' work that was at least the ones that got us to think about this. And I'm sure there's other papers as well there, but that's based on basically that technology there that's been documented in I don't know how many papers from her group. There is what we are implementing into Whitson Plus, and it will be a little feature down to the or just below the bottom of pressure feature in the software. So the problem is very simple. So like the easiest way for me to explain the problem would be, let's say you have a rate constrained wells, and we see this all the time in gas wells, all the time in liquid rich places as well, where we're constrained based on surface capacities. And you asked the question that Nils just got asked, how are what is this well going to produce? What's going to be its EUR? And you can't use ARPS for that. So you need a forecast, but how can you do it? And that's where PNRDCA comes in. So let's say we take this well that we just looked at, rate versus time. We only have rate data. Well, it's impossible for us to say anything because you can't, if you did this, you get a B factor of 10 or something. Huge reserves. It's going to be, constant rate for forever. Which actually, if you do thermal up in Canada, those wells are constant rate for a very, very long time. So that's how you would forecast them, but not very interesting. And then if we looked at the bottom pressure versus time, we'll get, a depleting bottom pressure over time. So the pressure is definitely declining as we're drawing down this well. But for whatever reason, this was a rate constraint well. So if I look at the initial reservoir pressure, what we call PI, and I take the delta between the PI and the PWF, I get this what we call delta P. And delta P, I can take the rate and divide by rate of delta P, or I can do the inverse of that. When I take the rate and divide by delta P, we get what we call pressure normalized rate. And then we're seeing, okay, this is actually declining. But for a lot of people that work with this type of unit system, especially if you do it for gas, you'll see, okay, the units to the left there looks very confusing. So a little bit of the magic that was done by the group at Oxy is to multiply the value on the y-axis. That a lot of you that done a lot of RTA, you work with pressure normalized rates all the time, so that's not something new. But what they did, just to make it a little bit more easier to maybe relate to for day-to-day engineers, was that they multiplied this with another delta P, okay? And here's important everybody pays attention, because this delta P star is the delta between initial reservoir pressure and a forecasted abandonment pressure, okay? So let's say that's 500 PSI or something. And what happens then is that on the y-axis, you get the units of barrels per day or MCF per day or whatever. And then just instead of plotting that versus time, we plot it versus cum. And in Whitson Plus, you will be able to plot this, fictitious rate, which is not it's not in rate time space, but at least it has the units of rates over day to get an EOR very quickly. And, there's no new, call it magical equations that we're using there. It's just ARPS in either rate time space or rate cube space. And if you've done a lot of that work before, if you've done it in Whitson Plus, you'll know how it looks like, something like this in rate time space. Also want to just mention, once you're starting to use this in practice, I had a session with Xueying on this, that at least in her experience in the Permian, they've had a lot of success of ignoring probably the first month before trying to establish a trend, just because the initial peak of your reservoir pressure can make some of the data early time be very sensitive to that. At least as a starting point, what she suggested was to use a B factor of 1 when they did a lot of the forecast there, and apparently that has worked great for her in the Permian. And also when it came to the abandonment pressure, the rule of thumb that they used there was 500 psi for pumps and 1,000 psi for gas lines. So that's a little bit of the background. So if we take this a step further now and try to come up with a workflow, it might seem easy because you would be like, oh, we can just fit this. Well, maybe you can, but we wanted to take a little bit more systematic approach to it. And as you all know, when you deal with forecasting, even if it's just a regular DCA, there is no way around what? There's no way around flow regimes. And that goes here as well. And the reason why I'm emphasizing that is even if you have PNR DCA, let's say early time, everything was infinite acting, and you forecasted that out forever with a B factor of 2, also in PNR DCA, you get the wrong result. Everybody, I think, is in line with that. So when it comes to flow regimes, I'm just repeating it here because it is important also in this context that we at Whitson, at least, we like to bucket the flow regimes into 3 different buckets. Initially, it's infinite acting flow, which means that none of the pressure transients have reached any of the reservoir boundaries. Then the total opposite extreme of that is what we call boundary dominated flow. That means that the wellbore pressure response is affected by all the reservoir boundaries. That's what we learn about in school as pseudo-steady state or tank-like depletion. So these are the 2 extremes. But let's say I've seen one of the boundaries, but not all of them. That's what we call transitional flow. And hopefully this will all make sense a little bit later. So if you talk about B factors at constant bottom pressure, for instance, infinite acting, a linear flow would be a B factor of 2. And then in real time, boundary dominant will be exponential. So that would be a B factor of 0. And transitional flow would be anything in between. So just, as a little reminder there. So how we can actually go about, trying to find the B factor to use, we could use one that was suggested as at least as a starting point and adjust it as you like. But could we try to come up with a little bit more consistent way of getting a B factor we should use? And that's what I've been thinking a lot about the last few weeks from a friend at Cotero that I'll talk about a little later. For those who haven't seen this plot before, this is just the fractional RTA diagnostic plot. Niels also showed that earlier, where we're just plotting the inverse. So we're plotting the rate normalized pressure versus time log. And we fit a power law through that, where this delta parameter right here is linked to the B factor. And you can also do PNR versus time, and you get this delta parameter right here. And this delta parameter, why is it important? Well, you can read all the fractional RTA papers about what it means physically, but in this context, we can use it to get a B factor. There's a direct relationship between the delta parameter and the B factor. Okay, so if we look at a real well, so this is how it's going to look like in Whitson Plus, by the way. So the PNR DCA is going to be below the bottom hole pressure right here. But if you just looked at semi-log, so basically the PNR rate versus cum gas, at least me, when I've been trying to do this on a lot of real wells, I've been asking myself, where should I start the segment? Like at what time, and what should the B factor be in that segment? Because if you look at this early time here, a lot of people would be like, yeah, we can maybe fit something there, and then maybe there's another trend here, etc. But very eyeball. I could potentially look at it in like a log plot, and maybe some of you done this so much that you are able to, that's the B factor of whatever. But could we take this and try to make it a little bit systematic? That's what we've been trying to think about. And that's where the fractional RTA diagnostic plot has been very simple. It's just rate normalized pressure versus time log. Where for this well, if I looked at it at early time, I would get delta of 0.5. A delta of 0.5 is a B factor of 2. That's how the equations work. And then if I was doing this type of work, I would say maybe time to linear flow is somewhere around here, maybe to the left, actually probably more to the left. But this other part of the data, maybe that's a delta that's slightly negative. And how the equations work out then is that will be a B factor of 0.96. So if I then plug those numbers into the PNR DCA, where I start the segment, I've answered that question. And, that might seem like a trivial thing, but, on the x-axis here, we're using cum gas, at least as a default. So it's not a trivial thing to necessarily know what that is in cum specs. The second thing is like, what B factor should you use? Well, you have the B factor there. And after that, you can just play graphically with what the decline factor is. And then some of you might be like, well, maybe something is happening here. Maybe the well is liquid loading. Maybe it's another boundary, or, maybe there's like, a transition from, linear flow into some kind of transitional flow and into some kind of other transitional flow, which happens because you're seeing more and more boundaries over time. So let's say that was true. Well, if I then looked at this plot again, initially I have 0.5, then I have this B factor of 0.96, and then I put my new start date. And here, the wording that they use is not, because it's not end of linear flow, but it's just end of characteristic flow. That's what they talk about. But if you have a better name, let me know, because it doesn't roll necessarily easy off the tongue. We can all agree to that, I think. But if I did kind of a best fit here, I would get a B factor of 0.76. So I would still do the same steps. I'll plug in my time to end up characteristic flow. Okay, that's a challenge to anybody that's good at marketing. Jessica, find me a new name, and then put in the B factor of 0.76, and you get an EUR. And I think you kind of understand the steps. That was very helpful for me, at least, when it came to maybe a potential workflow. This is kind of still out there, and to use the RMP plot to find the end of this characteristic flow. You can get the B factor out just by looking at the slope there, and then you're ready to just PNR DCA away. And Narayan from Coursera was kind of the first one to send emails and be curious about, should we or could we use this fractional RTA plot more actively in this workflow. And I think there's something to that, which again, this is very early for us. We haven't really done a lot of PNR DCA in general. So when we release it, I'm sure there's going to be a lot of feedback and maybe some good thoughts around how we can do this more consistently. The last thing I just wanted to mention real quick is this. We're doing it PNR DCA. It's a mix of rate and pressure. So it's not trivial to just get it into rate time forecast if you need that for like an economic evaluation or whatever else. So what Narayan, again, came up with as an idea is, okay, you do PNR DCA. This is just on another well, and you get an EUR. Okay, the EUR number is important because it is like, secondary opinion on what the EUR is, which is not pure DCA, etc. But what if you also forecasted out the bottom pressure versus time? Well, now you're actually able to calculate from the PNR some rates versus time, and you at least have a way to get the rate versus time data. We haven't tried this, but again, thanks to Narayan, I think there might be something here. I'm a little bit curious if people really need or want the rate time forecast as well. So kind of how we were envisioning it is like, okay, you either this is the default view, or maybe it's an advanced view or something like this, where we do PNR DCA and we have these helpful plots to the right where we can get the B factor of this, like, okay, when should I start my segment for the final decline, if you like. How do we get bottom pressures versus time, and what would that or what is our forecast of bottom pressure versus time, and how do we get our rate versus time data. So yeah, anyways, a lot of thoughts. We're not kind of presenting the final answer, but if you have really strong opinions about this, you have my email, and you need to let me know. Very good. I don't know if there was any questions. Well, it seems like a lot of questions, or at least two. Yeah, okay, yeah. So it was a question just about like using derivatives in general, and that is true. You can toggle on derivatives in any of these plots, and you can use that to evaluate or like get more confidence in flow regime changes and whatnot. The thing I always say with derivatives is like it looks beautiful in a textbook, in like Clarkson's book and whatnot, but the problem with derivatives is that their job is to amplify the signal, but they also amplify the noise, even if you use Bordet derivatives and all this fancy stuff. So in general, I personally at least don't really use it much unless the data is extremely clean. And Jennifer has a great question as well. Why is this workflow not also being used for regular DCA? The auto forecast seems to just be a single segment curve, which doesn't honor flow regimes either. This has been my hesitation with auto forecasting, especially in wells that are in linear or transitional flow for years. Yeah, that's a good question. I think the answer to why it's not used for like, for regular DCA, I think it's just because it's in a different time space. But I think that's what we're trying to figure out, if it's a good way for us to kind of bridge the gap between the two. And it's true what you're saying. If you have wells that are infinite acting for a very long time, well, this technique, but also RTA, all of these techniques, because you don't know what the tank size is. That's the definition of it. So in a scenario where you're still infinite acting for a very long period of time, it would be tricky to use any technique with certainty. If you're in transitional flow, which we see a lot in real data, is like a lot of these wells will be on, people call it power law type of behavior, which just is a fancy word to saying you're not really in true infinite acting linear flow, but you are on something in between that and boundary dominated flow for a very, very long time. And your assumption there, at least in the forecast, is you're not suddenly seeing all the boundaries and your beat factor goes to 0. So that's just also another thing to be aware of. Yeah. What happens when you do not have time for the end of characteristic flow? PNR objective is a preliminary estimation with a little less info. Yeah, so that's a good, to Horace's point there. What do you know if you don't know the time to linear flow, the time to characteristic flow? And it's like, what would you do if you did RTA? I think there we need to be honest with people who like us that do RTA. It's like, okay, what would you do if you had this challenge in RTA? Well, you would use permeability of other wells in the area that you have already history matched. And that's a way for you to implicitly say what the tank size could be to constrain a problem. And I think the same thing will go here, that you would probably use analogs or something like this if you did not, if you hadn't reached that end of that characteristic flow period first. Yeah. And Raul mentioned just a comment there, I guess, that they use, at least at Oxy, because a lot of the auditors, they would like to have a secondary way to in addition to DC, I guess, to have a EUR estimate. So that's how they've been using it at Oxy. And Samir, he asks a really cool question, which our friends from Javelin or Crescent Energy, Tucker and whatnot, presented at WitCon last year, which is basically creating type curves, kind of PNR DCA type curves. And I think there's something there. I haven't done any work on it, but maybe there is something interesting to investigate there. Yeah. And there's also a great comment from one that it's like, it's not a it's not a silver bullet. It's just a secondary way to get an early time estimation of EUR, and not necessarily the one and done. That's the answer for forever. Yeah, perfect. And then Stein Erik has a question related to noise reduction for like long-term DCA and RTA. So the short answer there is like there's a bunch of different typically kind of integral ideas there. So like you would do the rate normalized pressure integral, or if you did some kind of derivatives, you would use the Bourdieu derivative with different types of smoothing techniques. So very similar type of ways of reducing noise there. And I think you can even do the rate integral as well. So maybe that could be relevant here as well. But integrals has the opposite. They have the opposite problem than derivatives, where integrals, they would not only reduce derivatives, they try to reduce increase the signal, while integrals, they try to reduce the noise, but they also reduce the signal at the same time. So many times you have to use those at the same time. Very good. We are going to go to the also one mentions, can you comment on using a moving average behind the scene to mask the data that could influence quality of the fit? Yeah. So we're not using any type of moving average here, but I know that in a lot of auto forecasting packages, I think in Aries or Ovintiv, they have that, which have some people really like to actually fit the moving average and not all the data itself. So it might be something interesting to look into. We're going to be on kind of the auto forecasting step in general, and I'm going to get my colleague Mo to share his screen, and I'm going to also move the microphone a little bit closer to him. So Mo, can you share your screen real quick?
Yes, sir. Hello, everyone. I hope you can see my screen. Just move this out of the way. So I'll be talking a little bit about auto forecast, and you've probably seen the great presentation from Juan earlier today. So my presentation is going to be more about the functionality that it has and kind of how to use it within the software, because I know that many of you have been working on different parts of the software and have not necessarily gone very close to auto forecast. So I just want to give you an overview of the feature. With a great introduction from Juan, we all know what the problem is. Basically, every single well you have is going to need a forecast. And if you have a lot of data and you want to do like a first pass on a lot of data, that can be very, very time consuming when your data set is very large. So basically what you're going to try to do is going to try to get an auto forecast run on all the wells, which is basically decline curve analysis applied on every single well that you would have, done automatically. And you can use it for many different things. Many people use it, to try to characterize uncertainty. They run with different constraints to validate your manual forecasts. Most of the places I see, they use it to start as a starting point for their forecast, for their manual forecast. So they go and adjust it. And then you can also use it to, of course, build your type well data set where the production history is variable between the different wells. As a workflow, the auto forecast is fairly straightforward. It's 3 steps that you would have. You would have to initialize. You have to say, okay, what are the parameters that I want to use? What are the constraints? What B values I want to use? And some other things that I'm going to show you later. Once you do that, then you just run your AutoFit. And within that second step, you can also review the results, change different things, and export to multiple formats. And the final step is that you have like sort of a QC plot where you roll up all the results and you get the roll up of all the forecasts together with the historical data. So with that, I'll actually just go directly into the software to show you how that looks like. Let me see here. So I'm in a project here. It's a small demo project with about 20 wells. And auto forecast is going to be basically under the multi-well analysis. It's the first feature that you'll see down there. So each of these wells will have its own production data. And within auto forecast, if I click there, the first thing I can do is I can create different areas to sort of classify my auto forecast. So I could say, okay, I want to create a type well area that I'm going to call like my type well. And that's basically just to classify. It's like a folder structure. Within that, I can add an auto forecast. And now it pulls up basically all my wells, the list of 20 wells, and it's going to allow me to select the wells in different ways. I could just click on the wells individually, like I'm doing here. It will select them. I can also use a map, which we're also upgrading, like the GIS feature, but I could use the map to say, okay, I want to select these wells here, and I want to create an auto forecast for them. And you can also use the grouping. If you've already created groups, which many of you have done, you can also, of course, use the grouping to select and deselect the wells that you would like to add to your auto forecast. You select the type well area here, and then the first thing that you're going to see is the initialize step, which is basically now you have to set up. You have to say, okay, what do you want to do with this auto forecast? What are your constraints? Okay. Some of the basic options is, for example, okay, what is the B value that you want to have? By default, we allow you to have a B value that changes between 0 and 2. Let's say you were very fixed and you wanted a B value that was fixed. You wanted to run all the wells with a B value of 1. You can lock this value here, and that will run the auto forecast with a fixed B value. You can also change the ranges. So you could say, okay, I want to run the auto forecast on a range between 0.7 and 1.5 for B value. And that's kind of a very simplified way to run the auto forecast. And you have the options of how long you want to forecast for. You have the total production time, the cutoff rate for each of the phases, and the limiting effective decline for each of the phases. Once you've set up that, you can go to the next step, which is to AutoFit. And here on the AutoFit, you just get a list of all the wells that you've selected. And if you click AutoFit, it will basically run through a DCA for each of the wells. And here you see I did like 12 wells fairly quickly. With many people like Juan have used it for thousands of wells, and it's a very useful tool. But within each of the wells, you can see first the results for all the wells. You can kind of inspect the different B values that you're getting the right values. Inspect the EORs. You can sort by, for example, EOR. This is ascending EOR, and start to inspect all your wells. But then you can say, okay, maybe some of the wells, I just want to inspect them specifically. I want to go into one of the wells. So you can click on any of these rows here. That will take you to the DCA specifically for this well that was generated. And you can actually just modify this manually if that's something that you would like to do. So if you want to adjust the DCA a little bit up and down, whatever you do here, it's basically going to stick to the auto fit of this well as a manual modification that you have done. To quickly navigate between wells, there's arrows here to move to the next well. There's also a shortcut, which is to use page up and page down on your keyboard. So now I'm going to just click on my keyboard, page down, and it's going to switch between wells. So it allows you to quickly, let's say you have hundreds of wells, it allows you to kind of quickly browse through each of the wells to see which well do I want to pay more attention to. I want to adjust that forecast manually. So here I'm just kind of browsing through that. That's kind of the main thing that you would do with auto forecast. You have a lot of different options as well. By default, this is how you would see the screen to initialize. But you have different options like, for example, you can fit partial data. That basically is telling the algorithm, hey, I don't want you to go and find the best fit in your case, but I want you to, or for the whole data set, but I want you to focus on a certain percent of the data. I want you to focus, for example, on only the last 20% of the data. That's one way to do it. You can also tell the algorithm, I want you to focus on a date range. I want you to only look at the production data for, let's say, the last year, the last 2 years or whatever. You can fix the date range that you want, and then the autofit will focus only on that part. You can also say you want the last X days. That means, okay, I want to fit only the last 100 days, the last 200 days, whatever amount of days that you want, and then the algorithm also will do that for every single well. One thing that you also do, or people like to do a lot on the auto forecast, is you're forecasting your primary phase. In this case, these are oil wells where the primary phase is oil, but you also want to look at your secondary phase, which is gas. So within each of the plots, you'll have a secondary plot which shows all streams, but you can also switch to the actual decline curve analysis for that secondary phase here at the top, where you can click on the gas, and you're going to see basically the gas forecast. You can adjust that as well. But one thing that you could say, for example, you're exploring these forecasts for gas, and you might think, okay, actually, I don't like to do gas DCA when my well is an oil well. What I'd like to do is I would like to forecast on GOR for the secondary phase. And that's something you can also tell the auto forecast to do. So you go back to the initialize step, and you have an option here that says use different bounds. Let me just try to zoom in a little bit there. Use different bounds for each stream. And if you click on that, it brings in a lot of additional options. Why? Because you might have different B values that you want to use, or different parameters that you want to set for the gas phase versus the oil phase. But one of the interesting things that I like to do most of the time is to change the secondary phase forecast, in this case, the gas phase forecast, from being a primary forecast, so just an ARPS forecast on the gas, to a GOR forecast. And once you do that, you'll see that you'll get automatically set to another autofit type, not ARPS, but to a constant forecast. You can change that, and what we like to use in most cases is either a semilog or a power law for forecasting GOR. So as an example here, I could just go here, select power law, and what's going to happen here is now it's going to forecast my oil, and it's going to forecast my gas by using a GOR forecast with a power law. Okay, click continue here, and then I'm just going to have to run autofit on the wells. One very useful thing throughout Whitson Plus in general, but also specifically for auto forecast, is when you see this yellow exclamation mark, that means that basically something has changed on your data set. So you know that whatever you're looking at here is not updated with the values that you used to initialize. So you just have to click autofit again. It's going to run through an autofit for all the wells now. And if I go back here, now I'm going to see my oil forecast, basically the same forecast, but on the gas, instead of the gas forecast or the DCA, the ARPS DCA on the gas, I'm going to see a forecast for GOR, which is going to translate into a gas forecast as you see here. Okay, and that's very useful. And you can do exactly the same with a GOR forecast. You can page down on your keyboard, and it's going to basically browse through the wells. So it allows you to make sure that you are inspecting everything and you like everything, and based on that, you can make manual adjustments as well. So that's kind of the main part of the first step, the autofit step as well. And then the final thing that you would want to do is now that you've done the analysis, let's say you did it for hundreds of wells, you want to go to the last step, which is the summary. And here you're going to create what we call roll-up charts. So you're going to roll up all the historical data for all the wells, and you're going to roll up all the DCAs that were created for all the wells. And you just want to make sure that this makes sense, that there's no sort of very abrupt change in the trend that you are coming with on the cumulative oil or on the DCA for the rolled up. That you can do here, and you can select if you've saved multiple auto forecasts, you can basically compare the different ones here, just roll up with different auto forecasts in this case. One thing I forgot to mention here on the auto fitting part is that people like to export these values to basically like the DCA parameters to a bunch of different software, and you have all those options here. You can also simply export them to Excel if you're planning to just import them into a visualization tool or whatnot. And then the next thing I wanted to show you is within the DCA fit, one thing that we've gotten a request for is kind of the possibility of manipulating this decline curve a little bit more graphically. And that's something that my colleague Henrik has worked a lot on, and it's really getting a lot better and very slick. You have a set of shortcuts here that you can access. And with those shortcuts, you basically can learn how to move things around. So for example, if you wanted to shift the entire DCA segment, you can use this button. Like you can basically click here and it will basically shift the entire DCA up and down. Or as it says here in the shortcut, you can Alt, basically just click and drag there. There's also another one where let's say you were happy with the forecast, but you were not happy with where it started. You just don't want the start date to be back there. A lot of people wanted to be able to shift the segment points without altering the forecast, and that you can do. You can shift any point. You can shift. You pick the point you want, but let's say you wanted to shift the starting point here. So you can do that without altering any of the forecast, and you can do that also with the shortcut by using your shift on your keyboard. So that's basically just, it doesn't adjust any of the forecast, just adjust the starting point here. And as Juan very well pointed out, I also wanted to walk you through quickly some of the features that Juan and his team and some other clients also have been requesting related to this feature. Basically, if I had gone into a well and I had manually done the fit for the well, now you're going to have the possibility of seeing that the well has been manually fitted. There will be some new columns added, as Juan pointed out, producing months, EOR12, etc. And also it will be possible to, if you come next time to the same auto forecast, now you can decide that if I have already manually fit some wells, I don't want you to overwrite those. I want you to just keep them not, don't try to do an auto forecast on those. I want the manual forecast to remain. We're actually putting a lot more effort than what you see here into this feature. And as I said, my colleague Henrik, a big shout out to him for all his efforts into this feature. And some of the things that are coming that we're very excited about, at least that are worth mentioning here, is that you'll have the possibility of having customizable viewing modes. So you're not only going to be able to see the table in the AutoFit results, but you're going to also be able to see a 2x2 with primary and secondary DCA plots. We're also adding practically a statistics page for this whole feature, where you're going to be able to see plots of all the statistics that are relevant, and you're going to be able to filter through that. Like, you can select some ones and say, okay, I want to go to this well because I don't like that this is an outlier in terms of the statistics in the plot. And also adding a lot more things. Maybe also some of the things that you guys have been asking is, for example, doing auto forecast on PNR DCA, which is what Matthias talked about in the previous session. So with that, that's all I had to cover. Is there any questions?
It was just a question from about like the difference between like the EOR that we report, the remaining reserves, and the historical forecast. But I think we answered that in the chat.
Yeah.
We have 2 more presentations left, and we're really good on time. Wilson, will you be sharing your screen?
Yeah.
So, we're at the end of the session. We've covered a lot of production engineering. We've covered kind of RTA, DCA, forecasting. And now we're going to go to one of my passions, and Curtis Whitson's passion, and everybody at Whitson's passion, which is PVT. So with that, Wilson, we'll I'll stay muted.
Yep, so I'm going to be talking about PVT properties today. And so Ovintiv had the business need to understand and map PVT and fluid properties associated with our wells and be able to update these properties easily as more data became available. And the Permian Basin is what this is going to be based on today, but we've applied it elsewhere as well. I'm going to talk about the primary inputs into the equation of state, how we got them and the interpretations behind them, and how I used those to generate PVT maps. And if time allows, I'll talk about some of the key differences behind mapping PVT properties with an equation of state versus more traditional methods. So because we probably have a wide range of people and expertise here, typical PVT data, you will get formation volume factors, GORs, and oil viscosities modeled as the pressure depletes. So a PVT test is essentially a rapid test of what occurs over the course of many, many years in a well over the course of a short period of time on how the fluids change with pressure. To get this information, we typically need to have an initial GOR, initial pressure, and a reservoir temperature. From that, you can get the formation volume factor, bubble point pressure, reservoir fluid viscosity density, and many, many other properties, but those are the ones typically used in most engineering analysis that we do on a day-to-day and in almost any sort. And this is a map of the Midland side of the Permian Basin. The black sticks in the middle are all the wells that were there in 2020. And all the colored sticks you see are new horizontal wells that have been drilled within the 5 years past that, which kind of speaks to our company's need of being able to update our PVT maps quickly and easily as new wells get developed and new information becomes available. Because in the course of those 5 years from 2020 to 2025, most of the new wells some have been put in the middle of the basin, but a lot have been going out to the edges of the Midland Basin, which in case you don't know, as you start to go from the center of unconventional basins to the margins, that's typically where you see fluid and PVT properties transition a little differently. So one of the first parts of this process was to get our initial GOR. I developed some code for Ovintiv internally that will pick the initial GOR based off of the cum gas, cum oil plot that you see in the top right. And as Matthias will tell you constantly, engineers like straight line fits, which is what this is. And it's a volume weighted initial GOR because the cum oil and cum gas will advance further in the large volume months. So it essentially tries to capture the concept that if you have 1 barrel and 1 MCF of gas or 1,000 barrels and 1,000 MCF of gas, that's the same GOR, but the 1,000 barrel month is going to be much more impactful and a better representation of your reservoir. So the initial reservoir pressure, Ovintiv has run quite a few bottom hole pressure gauges in our wells. We've used IPR analysis to try to predict the initial reservoir pressure on those. And we've also correlated that to some defits that we've done in the basin. And we then utilized that massive bottom hole pressure data set to try to build an initial pressure model that correlates other attributes about the wells, such as how close they are to offset producers, the age, the depth, the fluid properties, and all of that. And we developed a model shown here on the right that will predict initial pressure relative to the source of truth being our interpretations. Initial reservoir temperature, we mostly used temperature logs with corrections on them to account for time that water was in the hole, the mud invasion, and all of that kind of stuff. I was not the expert that worked on this at Ovintiv, so not as intimately familiar with this part. But we did pull temperature readings from our electric submersible pumps and integrated all that into the maps that you see right here, which is the inputs into the equation of state, the temperature, the pressure, and our initial GOR interpretations. And now that we have our base data set to try to quantify our PVT properties, the next step was how can I use Whitson's equation of state to create mappable fluid properties. So I took valid range of temperature, initial pressure, and initial GOR across our area of interest, the Permian in this instance, like from 100 to 250 Fahrenheit up to, gave 16 different distinct values at 10-degree increment steps, have 31 initial pressure values and 269 initial GOR values. I did the GOR at finer resolution because it is, in my opinion, the most important input and most influential in the PVT properties. And that gave us a total combination of reservoir properties of 133,424 values. So I then went into Whitson and created dummy wells with those assigned pressure, temperature, and GOR values. And that's when Mohammed emailed me with his hair on fire because I was crashing Whitson's server when I put that many wells in it. But I then calculated the PVT properties on all 133,000 wells and exported that data out. Here's an example of what that looks like, where I just had a fake well at a set temperature, pressure, and GOR and got a full population of PVT properties out of the Whitson equation of state. At this point, I had now captured across a valid range of reservoir properties in our area of interest how the Whitson EOS was modeling the changes in the fluid properties. This essentially created a PVT lookup table for us to utilize as we map our wells. And this did a couple things for me, because I've had multiple people ask me, well, how is the EOS modeling PVT properties? And it was generally dissatisfying for people for me to tell them, well, you can go put your properties in Whitson and it'll tell you what they are for this one instance, but they were wanting overall trends and how things are varying in a more global sense. And so once I had all those runs done through the Whitson EOS, I could put them into Spotfire and I could start to create plots such as this that helped with the communication with people that aren't reservoir engineers at Ovintiv on how the PVT properties are being modeled. And as you can see on here, as you start to get to high initial GOR, such as 3,000, you start to see that pot belly shape in the differential liberation type plot here, with a formation volume factor that tells you that you're starting to get into a volatile type oil. And you can start to see some of how the relationships with temperature change as GOR changes as well. And you can extract some learnings from this and get some general rules of thumb in your head. And total GOR on the x-axis, total formation volume factor on the y. And in here, you can sort of see, like, as you get to lower GOR numbers, like 1,000, 1,200, 1,400, that your temperature has a larger impact on your total formation volume factor as you get less gas content. And you can start to extract little nuggets of information out of it like that. I'm now going to walk you through how I took that 133,000 PVT table and of EOS runs and translated it into a map. So in this example, I have a well that has a 1742 initial GOR, 171 temperature, and 3783 initial pressure. And the 4 rows below that are the equation of state runs with their values that correlate to the particular value on this well. And I essentially took the well total formation volume factor and calculated how much, through linear interpolation, how much the values are changing due to temperature by itself, pressure by itself, and GOR by itself. Using a straight line interpretation again, because I am an engineer after all, did rise over run calculations for one EOS to another, and got the delta in the total formation volume factor for GOR, temperature, pressure, and then calculated from our PVT lookup table what the total oil formation volume factor would be for my particular well. And just to validate this, I picked an example here of a well that was close to the bubble point, because that is going to be the one spot in this method where you can get a little bit more error as you see that kink in the bubble point. Even in that very nonlinear section of the PVT properties, I was calculating a total formation volume factor of 1.933 from my lookup, and Whitson was getting 1.929. So within the margin of error, and the bubble point pressure was very close as well. And then extrapolating this method in this slide through code where we have all of our values on all the thousands of wells within our basin, you can then extrapolate that out to PVT maps, such as this one where you have the total oil formation volume factor, viscosity, and then you can start to create maps such as where in the basin do you think you have two-phase initial conditions, such as the initial pressure being lower than the saturation pressure. Are there any, that's all I prepared for today. Are there any questions?
I'll just mention that that project with 134,000, Mo did not have gray hair before that run, so I can tell you that. It's funny because, like, when people run a lot of these calculations, if it's like in bulk mode or if it's through the API and stuff, like we see it, like we monitor that on our end. And we actually had a fun, I know there's a lot of Marathon folks on the call, and we actually thought KP had built a bot because he was running so many PVT calculations, but not from the API, but from the front end. But it turned out it was him manually changing inputs, like just extremely fast. So you have that as well. It's like the program, the API or bulk mode, but also people that just works incredibly hard. So a shout out to KP for that. If anybody has any questions about this, feel free to reach out to us. We've worked with a lot of you guys to do this for the basins you're in as well. So if we can be helpful there, let me or Mo or anyone else know. We are going to transition into the last presentation for today. And as I mentioned, when Matt was probably not on the call in the morning, is that I asked everybody when I was at the so-called HFDC here in Houston, what was the best presentation you saw? And everybody came to me and they said, that's Matt's presentation. That was really impressive. And I was like, okay, I need, first of all, Matt, a beautiful name. That's my Starbucks name. So I was like, I already like the guy. And then his presentations were amazing as well. So he's going to share this one with us as the final part for today. So Matt, if you can share your screen and unmute, that would be great.
Right. I just shared my screen. Let me know when you can see it.
Yep, comes through perfectly.
Okay, awesome. Well, good morning, everybody. My name's Matt Jones. I'm an engineering advisor for Oxy. I was not on the call earlier, but as you can probably tell from the title of this presentation, it doesn't focus on reservoir engineering or production analysis specifically. It gears much more towards completions. This was a presentation that I gave for HFTC, or the Hydraulic Fracturing Technology Conference, in February. And really what it is it's a collaborative effort that's been ongoing between Oxy and Dark Vision for the better part of 2 years. And we recently published the results of that effort in the paper titled Adding Depth, the Superiority of Volumetric Perf Erosion Analysis. Now, before I get into the presentation, I think it's important to just give everybody a sense of what the primary motivations of the work were and some of the key observations that were made. First and foremost, what we were attempting to do was to validate an alternative diagnostic tool to permanent fiber optics, which is currently the gold standard for completion optimization efforts. Permanent fiber is a phenomenal tool in the sense that it gives you real-time data collected at the cluster level. However, it is very expensive on a per well basis, and it can be prone to mechanical failure. Now, what we've seen is that when we perform volumetric perf erosion analysis, we actually get great alignment with permanent fiber optics, as you'll see towards the tail end of this presentation. And ultimately what this means for operators is that we can have better confidence in design decisions for substantially less cost. Another motivation for the work was that we wanted to evolve from basic 2D to 3D perf erosion analysis. Now, what we have typically seen in wells where we have both fiber optics and perf erosion measurements is that when we work with two-dimensional measurements or we do exit hole analysis only, it tends to lack alignment with the fiber optic results. So you're left wondering which tool you should believe. But with a lot of the advancements that have been made over the last several years in ultrasonic imaging technology, multiple measurements per perf are very easily obtained. So it stands to reason that if we can do a three-dimensional analysis rather than a 2D, we should. And what we've seen is that there's multiple ways we can compute perf tunnel volumes. The simplest method, which assumes a conical frustum or a partial cone, will suffice. We can improve accuracy by doing a more integrated approach and taking more slices through perf tunnels. I'll elaborate on that a little bit later. But really where this is going, and it's almost at a commercial point for Dark Vision, is point cloud generation to compute volumes with machine learning models. The last motivation for the project was we wanted to develop new perf erosion diagnostics. We wanted to be able to couple theoretical perf growth cases with empirical observations so that we could better understand erosional growth tendencies. To that end, we were able to create and validate a novel diagnostic plot, which we can use to see very distinct trends in perf erosion behavior when we look at entry and exit hole area measurements. But really what it means for perf erosion analysts like myself is that we can empirically determine uneroded perf sizes. Whereas typically we would have to shoot a set of unstimulated perforations in the heel of a lateral and use those as a baseline to compute growth. So before getting into the data, I want to start a little higher level and just talk about the evolution of acoustic perf imaging, where it started, where it is now, and also the conceptual stages of perf growth, because it's going to tie into some theoretical cases I'll show you on the next slide. Approximately 6 years ago, when ultrasonic imaging technology was first being introduced, the analyses that were being performed really treated perfs as basic circles, very fundamental two-dimensional shapes. But as more data was collected, outliers and anomalies that exhibited very eccentric growth behavior became much more frequent, much more apparent. What we've seen more recently is cases of what we would classify as perf beveling only, meaning that you've got some level of growth in the entry hole that's along the ID of the casing, but very little meaningful growth in the exit hole that's on the OD of the casing. Now, what we do know beyond a shadow of a doubt at this point is that perf erosion is fundamentally a 3D problem, not a 2D problem. Now, the way we visualize a lot of this is we assume that perfs initially start out as conical frustums or partial cones, whereby the entry holes along the inner diameter of the casing are larger than the exit hole on the outer diameter of the casing. Now, as we start to place proppant through perforations, we'll start to see some level of beveling, whereby we have some entry hole growth, but not yet any level of exit hole growth. As more proppant goes through those perforations, we'll start to see a level of stable growth, where we have proportional growth between both the entry hole and the exit hole. And in some cases, we can see runaway growth. That's pretty common in cases where perforations are shot in casing connections. So moving on to some theoretical growth cases, I'm going to use these to explain the development of the novel diagnostic plot. Over here on the right half of the slide, I have a matrix that considers different growth conditions for different growth cases. So to start out, let's talk about what the columns of this matrix represent. Each one of these columns constitutes a different ratio between the entry hole area and the exit hole area. This column on the left assumes an entry to exit hole area ratio of 1, meaning they're exactly the same. So as you can see from the images, this is basically a perforation represented as a perfectly uniform cylinder. The middle column represents an entry to exit hole area ratio of 2. So entry hole area is twice that of the exit hole. And then the third column is a ratio of 3. So this is kind of the more extreme growth condition. Now, each one of these rows in this matrix represents a different case. Case A in the top row assumes beveling only. So this is a case where we have entry hole growth exclusively, no change whatsoever to the exit hole. So as we move from left to right here, you can see that the entry hole is growing, but the exit hole is not. This is actually a common phenomenon of completion designs that have relatively low perf friction pressure. The middle row is case B, so this represents what we would consider to be stable growth. We have both entry and exit hole growth, but we have assumed a 10% rate of change for the exit hole. And that rate of change is contingent on the rate of change with respect to the entry to exit hole area ratio. So again, as we move from left to right, you can see that we now have exit hole growth and a slightly higher level of entry hole growth, but this is something that we would consider to be stable. Case C, the bottom row, assumes runaway. This is a scenario where we still have entry and exit hole growth, but now we've assumed a 20% rate of change for the exit hole. So just qualitatively looking at this, you can see how this is a more extreme growth case compared to case B and certainly case A. Now, when I move to the next slide, just try to keep case A in the back of your mind. So the case of beveling only, entrance hole growth exclusively. And let's think about what that data might look like if we generated a plot of entry versus exit hole area ratio on the y-axis and entry versus exit hole area difference on the x-axis. Now, each one of these cases that you can see in this plot represents a different initial exit hole diameter. So this dark blue curve on the left portion of the plot represents an initial exit hole diameter of 0.3 inches, so a relatively small perf size. The brown line on the right represents an initial exit hole diameter of 0.7 inches, so a substantially larger perf size. But there's two things we can see in this plot. Again, when we assume beveling only constant exit hole area, regardless of the initial exit hole diameter, all of these cases are going to exhibit straight line behavior, and the slope of the line is going to be contingent on the size of your initial exit hole diameter. So smaller initial exit hole diameters have steeper slopes, bigger initial exit hole diameters have shallower slopes. Moreover, when we plot the slope of these lines on the y-axis here versus initial exit hole diameter, we see that we actually obtain a perfect power law correlation. So two takeaways here. One is that when we have entrance hole growth only, on the plot of entry versus exit hole area ratio on the y-axis and difference on the x-axis, they all exhibit a linear trend, and the slope of that line is going to be contingent on the initial exit hole diameter. Entrance hole growth only is more of an exception rather than the rule, so let's introduce some variable exit hole behavior. When we do that and we look at the same plot of entry versus exit hole area ratio on the y-axis and entry versus exit hole area difference on the x-axis, we can see that we start to see some cases exhibiting curvature. So this straight line over here is the 0% rate of change case, the entrance hole growth only case. But when we introduce rate of change, you can see here, when we assume 10% rate of change, that there's some deviation from the straight line case and some curvature. This teal curve on the bottom assumes a 50% rate of change. So the takeaway here is that when we have exit hole growth, we will start to see deviation from the straight line case in the form of curvature, and the degree of curvature is controlled by the exit hole behavior. And when we marry all those concepts together, it lets us create this diagnostic plot that I'm showing you on the right. So again, it's entry versus exit hole area ratio on the y-axis and entry versus exit hole area difference on the x-axis. The origin of this plot, which is a ratio of 1 and a difference of 0, represents an uneroded, perfectly uniform perf tunnel. The straight line on this plot, which is anchored at the origin, represents entrance hole growth only, and the slope of that line is controlled by the initial exit hole diameter. Now, as we start to see exit hole growth, we'll see departure and deviation from that straight line in the form of curvature, and it may initially be minimal exit hole growth, followed by moderate and eventually extreme. Any points that reside above this line are going to be perforations with an abnormally small exit hole diameter. So big takeaway from that is we can very quickly and easily observe trends in erosion data, and we can also empirically determine the initial exit hole diameter for a specific set of conditions. So let me demonstrate that for you. So this data that I'm showing you on the plot is from a well that we completed in Powder River Basin that was equipped with both permanent fiber optics and had perf erosion data collected post-frac. Now, the perforations that I'm showing on this plot, and by the way, each data point is a single perforation. These perforations are from multi-perf cluster designs that were shot in borehole sextant 1, which means it's shot towards the upper half of the casing. So again, we still have the area ratio on the y-axis and the area difference on the x-axis. I have fit the straight line to this data. And I've also called out several data points of interest, which I've labeled here as A, B, C, D, and E. Now, before we talk about the data points, think back to the power law correlation I showed several slides ago. The slope of this straight line should tell us what the initial exit hole diameter should be for perforations under this criteria. So according to that power law correlation and the fit of the data, it suggests that the initial uneroded exit hole diameter for perforations falling into this category should be 0.44 inches. Let's look at data point A. So point A is close to the origin, which means it should be an uneroded perforation based on the theoretical cases. When we look at its downhole image, we can see that it does have an exit hole diameter of 0.44 inches and a relatively similar entry hole diameter. Let's look at perf B. Perf B lies above the straight line and to the left, which again, according to the theoretical cases and the diagnostic plot, suggests it should have an abnormally small exit hole diameter. And when we look at it, it definitely shows that. It shows that it's a much smaller diameter on the exit hole compared to data point A. I should point out that both points A and B come from stages that were known to have been left unstimulated due to issues pertaining to the fiber optic cable. So we know that these are uneroded perforations. So it's definitely reasonable to think that the initial exit hole diameter should be 0.44 inches. So far, everything's playing out according to the theoretical cases. Now, let's look at perf C. So that has a high magnitude of both ratio and difference, but it lies on the straight line, which means it should be a perforation that has experienced entry hole growth exclusively while retaining the same initial exit hole diameter. So when we look at it, you can see that it still has the same exit hole diameter as perf A, indicating, okay, we have not seen any exit hole growth, but we can see growth with respect to the entry hole. If we look at perf D, which is, it's got a high difference, but it's below the dashed line. So this would suggest that it's been subjected to stable growth for both the entry hole and the exit hole. When we look at its image, we can see that that's the case. We've experienced growth in both the exit hole and the entry hole. The last data point E, which has a low ratio and a high magnitude, according to the theoretical cases, should be a runaway perf with extremely likely extremely eccentric growth in both the entry hole and the exit hole. And when we look at its image, we can see that that is absolutely the case. So this is how we validated this diagnostic plot. And again, it's very useful for quickly identifying trends in perforation growth behavior. But perhaps more importantly for perf erosion analysis is it allows us to empirically determine what the uneroded reference perf measurement should be. So if this line can be fit to the data, the slope of this line is contingent on the initial uneroded exit hole diameter, and I can reasonably determine a minimum entry to exit hole area ratio, well, then I have all the data points that I need to estimate both the exit hole and the entry hole measurements. And I can do that for diameters, areas, or volume. So let's move out of diagnostics and talk a little bit about how we're calculating perf tunnel volumes. As I said earlier, we generally assume the geometry of a conical frustum or a partial cone, where the entry hole along the inner diameter of the casing is larger than the exit hole on the outer diameter of the casing. This is the equation that has been used up until this point to calculate the volume of a perf tunnel. In this equation, H is assumed to be the nominal casing thickness. So just as an example, for 5.5 20-pound, that would be approximately 0.36 inches. Uppercase R is the entry hole radius, lowercase r is the exit hole radius. Now, in the paper that we published, you may see this type of calculation referred to as C2 or C2 geometric. Essentially, all it means is that we're taking two slices to calculate the perf tunnel, one at the ID of the casing, one at the OD. As you can see, this tends to systemically overestimate perf tunnel volume because it assumes a linear relationship from ID to OD. But in a lot of cases, there is a degree of beveling. So this will overestimate volume. We can refine this by introducing another slice at the midpoint of the perf tunnel. So this would be what we would call a C3 geometric. You still have a little bit of excess volume. Okay, fine. We can further improve it by adding more slices. Still have a little bit of excess volume, but notice that it's mostly located close to the inlet of the perforation or the entry hole on the inner diameter. This would be what we would consider to be the C5 tapered approach, whereby we have a higher frequency of slices through the perf tunnel near the entry hole. And this was found to be the most accurate method to calculate perf tunnel volume manually. So all of these methods are done manually. Where Dark Vision is going and is almost there from a commercial standpoint is using machine learning models to do point cloud generation, surface preening, and eventually volume generation. One of the things that Dark Vision did do in the course of this work is validate their acoustic tools measurements against a metrology grade laser scanner. So this was done in a laboratory setting. Here's a photo of a casing sample that had perforations placed in it and was subsequently sandblasted. And you can see that it's to different degrees. Beneath that is a laser scanner rendering of that sample. And beneath that, we have a cross section of the acoustic rendering. What was found was that the difference or the variance between area measurements from laser scanner to the acoustic tool was less than 2%. So that is a pretty high degree of accuracy, but the big difference between a laser scanner and the acoustic tool is that a laser scanner cannot be run in a downhole environment, whereas the acoustic tool obviously can. So good degree of confidence in the measurements being obtained from acoustics. When we compared the different calculation methods between machine learning, C5 tapered, which was the most accurate manual method, and the C2 geometric, just your basic conical frustum, we can see from two different stages that were from that permanent fiber optic well, there's no major difference. The values do differ slightly, but directionally, you would infer the same type of treatment using the different calculation methods. So obviously, we would like to work with the machine learning calculations at some point moving forward in the future because they're the most accurate, but just doing a basic C2 conical frustum method will suffice as well. So for that permanent fiber optic well, we did not shoot a set of reference perfs in the heel. Main reason for that is because the orientation of those perforations would have been subjected to whatever the orientation of the fiber optic cable was, would not have represented a good baseline to calculate volumetric growth for stimulated stages. So we actually used that novel diagnostic plot to empirically determine our uneroded reference perf measurements. And we were able to do this for every borehole sextant according to the multi-perf cluster designs because we had sufficient data points to do that. For some single perf cluster designs, we didn't have enough data points to do that by borehole sextant, so we had to assume that they were all uniform. But the reason I'm showing this plot here is because this is typically what we would see with actual reference perf data that has been measured, whereby we see some level of variability as a function of borehole orientation. So if we look at the entry hole diameters, which are shown here in orange, you can see that they tend to be smaller towards the top half of the casing and they get larger as you rotate around to the sides and to the bottom. So the empirical determination is very similar to what we would expect to see if we actually measured them. Now, when we want to compare different diagnostic tools, it's important to ensure that we're comparing similar metrics. So one metric that we use very routinely for fiber optic projects is proppant uniformity index, or PUI. It's calculated as 1 minus standard deviation over mean, where standard deviation and mean pertain to proppant percent allocations determined from DAS, or distributed acoustic sensing algorithm. So that's what we use for permanent fiber. With volumetric perf erosion analysis, we can compute a very similar metric, which we have termed VUI, or volumetric uniformity index. It's basically taking the volume of growth per perf, summing that up to the cluster level, and then representing the volumetric growth per cluster as a percentage of the stage. And then we calculate VUI as 1 minus standard deviation over mean, where standard deviation and mean are the percent of volumetric growth per cluster. So you can see that PUI and VUI are very similar metrics. So if there's any truth to these tools giving you the same answer, these would be the metrics you would want to compare against each other. One point I do want to make out, and we touch on this in the paper, is that when we do these calculations, you have the choice of doing them at the perf level or the cluster level. Because you're using an equation that uses standard deviation, it is going to be impacted by sample size. So when you do the calculation at the perf level, your sample size is going to be larger than it is for the cluster level. So this is just a word of caution for anybody who ever does this type of analysis. I usually recommend doing these calculations at the cluster level to maintain similarity with fiber optics, which gives you measurements at the cluster level. But ultimately, it's up to the analyst. At a minimum, we just recommend a level of consistency between analyses so that your results aren't conflated. We also spend a little bit of time in the paper talking about the significance of initial perf size consistency. Ultimately, what we have seen with data is that the more consistent you can get your initial perf sizes, the better off your final treatment uniformity is going to be by the time you've placed all of your proppant and fluid. There's a lot more details that go on in the paper for this, and this is really more focused on completions, but there's a ton of effort that I know we as Oxy put into on trying to ensure that our initial perf sizes are as consistent as possible, because that serves as your starting point for final uniformity. Okay, so getting into diagnostic tool comparisons, and I know I'm past 20 minutes here. On the left, I'm showing the results for fiber optics being plotted against PUI on the y-axis here. And on the right, I'm showing the results from volumetric perf erosion analysis. So we're plotting VUI on the y-axis here. Now, these are from the permanent fiber well we completed in Powder River Basin. And without going into all the details about design differences, essentially as we move from left to right in these box and whisker plots, we are increasing stage length and increasing the number of clusters per stage while keeping cluster spacing consistent. Now, from other tests we've done, we would expect to see a decrease in uniformity as we do that. As we increase stage length, as we increase the number of clusters per stage, we expect to see a drop off in uniformity. So if we walk through this relatively quickly, we can see that when we go from the shortest stage length, add 2 clusters, slightly increase stage length, we can see that decrease in uniformity. We see relatively similar results when we add 2 additional clusters, but when we make a change of going from multiple perforations per cluster to a single perforation per cluster with a slightly larger hole size, we can see an uplift. So everything between the green design and the orange design is exactly the same, with the exception of the perforating strategy. So we see an uplift. When we go to a longer stage length, we can see the drop off again. But when we make that change of going to multiple perforations per cluster to a single perforation per cluster, we can see the uplift repeat itself. This last design is a bit of an outlier. It happens to be the only design in the analysis that has all stages shot in the upper half of the casing. All these other designs have at least one stage shot in the lower half. And we know from this test and other tests that we've done that perforating in the upper half of the casing tends to improve uniformity. So that's what the fiber optic story is. If we look at the perf erosion story, it's essentially the same, albeit with slightly wider margins. We can see that same drop off going from the shortest stage length to a slightly longer one, relatively similar performance as we increase again, a slight uplift going from multi-perf to single perf, the drop off again, the uplift from multi to single again, and this guy's still being a little bit of an outlier. So my point in showing you this is that we would make the same decision with both of these data sets independently. I would not come up with a necessarily different conclusion using one data set over the other. But where this has been the most impactful for me is when we look at individual cluster level hydraulic fracture profiles. So when we look at the permanent fiber optic profiles for 2 different stages, and by the way, these go from heel cluster to toe cluster, top to bottom. So these are the permanent fiber optic profiles in green. These are the volumetric perf erosion profiles in orange, and these are the profiles overlaid. You can see that there's a tremendous amount of similarity between these 2 diagnostic tools. Now, when I've tried to do this in the past with wells that have similar data sets, but the perf erosion data is 2D rather than 3D, I cannot get this level of alignment. So just to recap, when we work with volumetric perf erosion analysis, we get great alignment with permanent fiber optics. And the fundamental difference between those 2 tools, outside of what the tools are sensitive to, the real-time data difference, is the cost. We could probably do 4 wells using volumetric perf erosion analysis for the single cost of a permanent fiber optic well. And this gives us better confidence in design decisions for less costs. As I showed you, there's multiple ways we can compute perf tunnel volumes. Even using a simplified geometry is still sufficient, but this is going in the direction of machine learning models. And as I also showed you, we were able to generate a novel diagnostic plot that not only gives us the ability to quickly see trends in data, it also lets us empirically determine uneroded perf sizes, whereas before, or if we work with 2D data, we're completely at the mercy of whatever our reference perf measurements are. Just to wrap it up, because this was a published paper, I would like to extend thanks and acknowledgments to my co-authors, in particular, Charles Bourgeois with Dark Vision. He and I had countless conversations over the last 2 years on what this data means and what can we do with it. Also, thanks to Oxy and Dark Vision's leadership for letting us publish this work. And last, but certainly not least, huge amount of thanks to all the perf erosion pioneers, men like Dave Kramer from ConocoPhillips, who have really worked over the last 40 years to get us to this point. We're simply taking what has been done over the last 40 years and trying to progress it to that next step. With that, that's all I had to share this morning. Open for questions if anybody has any.
Awesome. That was great. It's great, Matt. No, very, very good. The understand why people are excited. If you go back, you said you worked on this for a couple of years. Is that right, kind of ish? It's been an ongoing effort for a couple of years. If you go back to Matt Jones, anno 2023, and his, mental models, etc. What would you think is like the best or biggest difference between Matt Jones 2023 versus, today after these learnings?
I would say that when I worked with the data sets prior to the addition of entry hole measurements, it was obvious just qualitatively looking at it that we were not fully capturing or describing erosional behavior. There were many times where I would look at a report and the reported value of an exit hole diameter was basically the same as what an uneroded perf would suggest, but you could see a degree of beveling that was along the inner diameter of the casing. So we knew that there were likely a lot of cases where, a report suggested that maybe treatment uniformity was very low. There were very few clusters that took proppant, or there was a tremendous amount of bias. But being able to see those changes and not fully compensate for them was incredibly frustrating. I think really for me, the bigger question I've got right now is when we look at this type of data, is perf growth, whether you do it from a 2D perspective or a 3D perspective, is it correlated with the volume of proppant that went through it or the amount of kinetic energy that was imparted to it? Like if I go back one slide here, when we look at these types of profiles, we generally assume, as you can see from the axis title here, that this is the volume of proppant that went into each of these clusters. My next question is this actually correct in terms of proppant placement, or is this more a function of fluid placement or aggregate slurry placement? So I think we've done a ton of improvement on just giving ourselves better measurements, but I think we need to do some more investigative work to better evaluate the data and fundamentally understand what does it mean from a proppant placement standpoint, because that should be correlated with production response. Where did the proppant actually go?
I think this was a perfect way to end the day today. It's been a lot of technical content. We were on time for once, and people, if I told that to people before the session started, there will be no way with Matthias running this. It's always going to be over. But here we are, 10 minutes until 12. And I would like to thank you one more time, Matt, just for contributing here today, and for all the other speakers that have been providing both content and good discussions throughout the day today. So with that, we'll end the meeting. And if anybody have any follow-up questions or whatnot, just follow up with us over email.